All right, so am I good to go? So, okay, cool.
Um, so, welcome. This is a talk on Clifford numbers. This is Benjamin, or
Brandon.
Brandon, sorry.
Yes, yeah.
And yeah, he's going to be giving a talk, and I will be giving you 10 and 5 minutes.
Okay, thank you. Yes. So yes, hello. My name is Brandon Flores, Brandon Force on GitHub, and yeah, I'm going to be talking about cliffordnumbers.jl today, a package I've been working on for past 2 years, but I honestly did not anticipate giving a talk about it at JuliaCon, to be honest. So yeah, thank you for coming out here. So let's start off, and I'll just tell you a little bit about myself. So I'm a military brat. I was born in Beaufort, South Carolina. I've been raised across the country, though I've never been up to Pennsylvania before. This is my first time up here. And I ended up going to UC San Diego for my bachelor's, and I learned a lot about inorganic chemistry. I got my BS in chemistry there. Really took a liking to crystallography and related topics. And now at UW, Madison, forgot there's two UWs. I'm a PhD student there. I'm a computational chemist. I'm working at the Scalable Systems Lab in the Department of Chemical Engineering. In my spare time, my friends refer to me as a hobby collector. I could go on forever about this, but I know I've got a limited talk slot, so I'll just tell you about one thing I'm working on, which is astrophotography. That is my telescope, and here is an image I've been working on, which is an infrared image of Messier 24. If anyone here is using Julia for image processing or astrophotography, I would love to hear from you, by the way. That aside, let's talk about vectors. In fact, let's use some Julia parlance and take vectors seriously. Again. So back in the 1840s, William Rowan Hamilton wrote his famous equation, I squared equals j squared equals k squared equals ijk equals -1, and he came up with the quaternions. And the quaternions are a very interesting mathematical construct. They're a division algebra, which means that everything will have an inverse. You won't be left with things that don't have inverses in this algebra. And any of you here work with computer graphics at all? I assume you might actually have used quaternions and/or struggled with them. I know that's a very common rite of passage for computer graphics, and it allows you to compose 3D rotations very efficiently. But the quaternions are a bit weird, and one of the bits of weirdness is that they're non-commutative. So, ij doesn't equal ji. That one is ij equals k, but ji equals -k. So in the time that quaternions were used very heavily, people were frustrated with them. I mean, James Clerk Maxwell wrote 20 equations to start describing electromagnetism in quaternions. This was later replaced with the vector algebra formalism of Josiah Willard Gibbs and Oliver Heaviside. And you get two different vector products. We all know your dot product and cross product. It plays very well with matrix math. You can do linear algebra. This is how we do a lot of different tasks in computing. Though the one thing you're giving up here is inverses. You don't really have the nice division algebra properties of the quaternions. And eventually, Hamilton's formalism kind of got relegated to being a niche formalism, and the vector algebra is what we use. And the vector algebra war was won by Gibbs and Heaviside. Except for a select few of us, this war still goes on today. Because one of the limitations that both of these formalisms have is that they're very three-dimensional. Try defining a cross product in anything other than 3 or 7 dimensions. It kind of doesn't work. The better way is to use something called geometric algebra. Quick show of hands here. Raise your hand if you've heard of it. Raise your hand if you've used it in some of your research or anything you're doing. Cool. I'm actually glad to see so many hands up. So this starts off with Hermann Grassmann's exterior algebra, where you have linear combinations of k blades. So each vector is going to be a 1 blade, and you take wedge products between them. And the property of the wedge product is that it's anti-symmetric. Two vectors, or the same vector wedges with any multiple itself to be 0. And then you get these higher order blades by wedging together different vectors. And so this is very similar to things like cross products and determinants, though it generalizes to any number of dimensions. And it, of course, is not going to be commutative because you have A wedge B and B wedge A. Your magnitudes are going to define an area of a parallelogram. That's a common way of describing it, though it's going to change sign depending on which vector comes first. So it gives you an idea of orientation as well as area. Now, from that, William Kingdon Clifford devise the geometric algebra. And you get one of these by extending your exterior algebra to include essentially, well, if you read any terminology, you'll hear symmetric bilinear form or quadratic form. Just think of it as a dot product. And when you add in a dot product, then your combinations of vectors that are identical end up becoming scalar values. So you get these mixed grade objects that are going to be scalars and perhaps blades of different orders, just a sum of them. And each of these are going to describe composed reflections. So if we think about a reflection like in a mirror, right, you have a vector that ends up being reversed by a reflection, and of course you have a plane that's kind of where the mirror is. And so each vector describes a reflection, and multiplying with a geometric product composes these reflections. And so with this combination of tools, you can do a lot of really cool things. You can create geometric constructs that span greater numbers of dimensions using your wedge products. You can compose transformations in terms of reflections or rotations or other higher order transformations. And then you can apply these transformations to any sort of object that you've constructed. You can even rotate rotations. The composition of transformations is one-sided, and the application of transformations is two-sided. And I would say the last formula is really interesting because you might want to think about where you see similar kinds of formulas throughout other work that you're doing. So the geometric product comes with some interesting consequences. You do have inverses, not for every particular object that you can construct, but for the blades and the versors that you get, if they square to something, and by squaring we just mean performing to geometric or the geometric product of a blade with itself or a versor with itself, then you can get an inverse just by dividing by the magnitude of this object, and it extends to any number of dimensions as long as things don't square to zero. Depending on your algebra, that could happen, but there are ways of getting around that. But I do think the most interesting case, or I guess purely mathematical thing to think about, or consequence of this geometric product is, this is the one time I'm going to ask you to do a little bit of math here. Let's take a E1, E2. We're going to say that these both square to 1 each, like E1 and E2 both square to 1, and that they are orthonormal. So that means that they have a wedge product that is not zero. If we square these, you can use a couple of properties of the algebra to figure this out. If you reverse the order of any two orthogonal blades, that's just the same as taking a negation, so that you end up reversing the order and putting a negative sign in front. Clifford algebras are associative, so we can just regroup our parentheses, and we find, oh, E2, E2, they're together now. And then we can just say that that's equal to 1, because E squared equals 1, and then E1 times E1 is also 1. So now you have an element of this algebra that squares to -1. That's really useful, right? You get the complex numbers essentially for free. And you might see some literature, some work that refers to complexification of Clifford algebras. But in many cases, you don't even need to do this. This complex construct is there, and it has a geometric interpretation. Now, as a broad overview of what you might see in a Clifford algebra, right, you can have scalars. Obviously, these are just zero blades, or you'll find these in any algebra. And you can go up to getting your vectors that you can use to generate the algebra, and then you can take wedge products between them. But you can only do so up to the maximum dimension of the space. So in 2D space, you don't have anything higher than a 2-blade. And in 3D space, we can go a bit higher. Now, Clifford algebras are what are called Z2 graded algebras. And so we can actually create a new algebra by just taking the even grades. And what's really interesting is if we saw that E1 and E2, E2 squares to -1, you get the complex numbers out of the even subalgebra of 2D space. And you get the quaternions as the even subalgebra of 3D space. So those we often think of, we think of the next step on as being the octonions, the Cayley-Dickinson algebras. But the Clifford algebras are kind of the geometric extension to this. You can then combine things in 4 or higher dimensions, and you get a consistent way of working with the geometry that's constructed by these vectors. I'm going to just very briefly go through some of the other operations you might see in some of the symbology. There are these involutions that we use. So there's the main involution that just negates all of your vectors. So you just reverse the direction of all of them. and we just denote that often with a star, a superscript star. And then there's the reverse or add. It's kind of like an adjoint of a matrix. It generalizes that, or like a complex conjugate. And together, if you perform both of these, you get something called the Clifford conjugate. So you might see this in a formula that comes up here, or in some literature on Clifford algebras or geometric algebras. One other operation I think is important to mention is that the top grade element of this algebra is often called a pseudoscalar. There are different ways of referring to this. You might see a Blackboard 1 or just capital I. I use Blackboard I for this. And what that does is it reverses all of the grades of the algebra. Assuming it doesn't square to 0, but that's its own special case. This is a very useful thing to be able to do because it allows you to construct kind of duality within the algebra, and it allows you to come up with new interpretations for objects or dual interpretations of objects. Now, there are many different ways that we can use the Clifford algebra, and the most common model you might see is something that's called vanilla geometric algebra. You may also hear it referred to as vector space geometric algebra. That's a term that's not really being used as much just because all geometric algebras are vector spaces. But this is basically, you can drop in and replace things like cross products with wedge products. You can, if you know how like cross products create pseudo vectors, in 3D, those are just bivectors. You just get these areas that have their own properties and don't behave like normal vectors. So there is, you can reduce the number of like exceptions and special cases you have with vector algebra. You can also very easily extend this to space-time and do relativistic physics with Clifford algebra. In fact, that's where they kind of got their start as a tool for physics with Paul Dirac. Though not in the form that I'm presenting to you, because that's usually based off matrix representations. But one of the really nice things is, you probably all know Maxwell's equations, which are 4 of them. I mentioned earlier that the quaternions, there are 20 different equations that you have for the, in that formalism. How many do you think there are in geometric algebra? The answer is, it's just Maxwell's equation, singular, which is really beautiful, and it can be solved like almost any other differential equation in this form, which is really nice. There are other models too. The one I think that's become really popular is you have projective, or we often will say plane-based geometric algebras, which map the like linear equations of the form ax plus by plus cz, or whatever number of dimensions you have, to a particular vector. So we take our vanilla algebra and we add in one degenerate dimension. So we have, if we have our Clifford algebra, that's the first term, n, is just going to be the number of dimensions we have. The 0 is number of negative squaring dimensions, and the 1 is that one degenerate dimension that we add. And using our wedge product and other tools, we can perform any sort of transformation or work with any sort of like points, lines, planes, their generalization to whatever numbers of dimensions you'd like. And the other one model that's, I guess, it's been popular in the past. I think PGA has taken over, but it's still very much worth mentioning, is conformal geometric algebra. And this lets you generalize different constructs in, say, Euclidean geometry to an algebraic setting, which is a really beautiful thing to be able to do. And you can do it in, as with all of these cases, any number of dimensions. You add 2 extra dimensions. One is positive squaring and one is negative squaring. And when we talk about this, and I wanted to like start actually talking about what's in the package and how you'd use this, I provide different data types. The one we're going to see the most in this talk is going to be the k-vector type, which represents linear combinations of these k-blades. Not every k-vector is a k-blade, but that's its own technicality I can answer questions about if you have them. And for a data structure, and almost all of the ones we'll talk about or that will be included in this package have the same type of structure. We have a grade operator, or sorry, grade parameter, which is not always present, but in the case of a k-vector type, you do need to know what grade it is. Q represents our algebra, and there are many different types that of algebras that we permit as, or that we provide in the package. And then the numeric scalar type, which is any subtype of real or complex, since you can create a Clifford algebra out of either of these scalar fields. And then you'll have a length type parameter, which is constructed from the algebra and the grade, if that, whenever that is known. And that's often omitted because we can, like in constructors, we won't use that. That's just redundant in many cases. We also have these even and odd types, which include all even grades and all odd grades, which are really the workhorses of the algebra. These are all of one of the nice things about that Z2 grading we talk about is that you can often, like if you work with a Clifford algebra purely geometrically, you can stick to just using the even and odd grades, which saves you about half the space of a full-sized Clifford number, which is something that I think is a big advantage. So things that, if you have 16 elements in algebra, you really only need 8 of them at a time. So let's talk about a way of actually using this package. So I know you've probably at some point in your life solved systems of linear equations. And we usually do that by doing left division with a matrix. You've all seen something like this. You've probably done this before in your code. But there are some cases where this may not work, because you might have equations that are linearly dependent, or you might have equations that are not consistent. And if you do this with just base Julia's linear algebra support, you get an exception, which is what you would expect. Since these are singular matrices, you can't take an inverse of a singular matrix. But there's an alternate approach that we can take using projective geometric algebra, because every linear equation will map to a one-blade or a vector in this algebra, and we can actually just find where they intersect using the wedge product that we talked about earlier. And so with our linear equations being one blades, their intersections being wedge products, and you have a one blade and one blade, these are two blades. And if we think about how to actually write this as code, we can just use a k-vector object and have the k-vector type use that to represent our equations. So by convention, the first term is actually going to refer to the constant. So in the very first k-vector, like 5 is actually the constant that x plus 2y equals, then you get the coefficients for x and y. So it's reversed from how we usually present these equations, but that's because the first term is actually the E0 term that squares to 0. That usually goes first in these representations. And we end up getting a 2-vector out of this, or a 2-blade, since we wedge them. And it will also handle cases where you have linear dependence or inconsistent equations very easily. If you have a linear dependent pair of equations, if they're just scalar multiples of each other, then the wedge product of any vector with a scalar multiple of itself is just 0, which is really convenient. You can just test for linear dependence that way. If you have inconsistent equations, you actually get a non-zero object. And the significance of this object is actually kind of important. In the first case, we have this term that has E1, E2 factors. And those E1, E2 factors describe a kind of weight for this point. And you will usually divide out the terms that you get here by the E1, E2 factor, just so that equals 1. And so you can recover your coefficients for this equation. But in the case of the last equation, we actually don't have an E1, E2 term. And what that tells us is that the equation actually involves 2 lines that intersect at an infinite distance away. Since you can't divide coefficients by 0 necessarily, but projective geometric algebra allows you to represent this case and actually give you a direction in which the lines will go. Now, one of the other things that you can do is, if you have these terms, since any term with E0 in it squares to 0, you can just square any of the results of these equations to figure out if they square to 0. And if they do, then you know that you have a case that may not be handled, you may not want to handle in the same way. But you can do so without invoking exceptions that you would get out of linear algebra, which is really nice. One other thing you can do that's, I think, even more powerful is, let's say you have an underdetermined system of equations. So we think about these as maybe like two equations that are planes, and they intersect at the line. Now, if you do left division in linear algebra, you will get one solution. You get the point with the smallest Euclidean distance away from the origin point. But if you do this in a projective geometric algebra, you get something different. You actually get the Plücker coordinates of a line. So you get a representation of the set of all possible solutions to this particular underdetermined case. which is a really nice construct. And one thing I will point out that I find like this is intentional in the architecturing of the package is that if you have integer inputs, you'll get integer outputs. So you don't have to convert to floats to do any of this, which might be useful if you have any reason to work with just pure integers for this. One other thing that I should point out here is performance. So let's actually do this first problem on a fair footing here and use static arrays to evaluate this. And we find that it takes about a microsecond. And we see that there's a lot of allocations. So that's, I believe, I'm actually no expert on linear algebra and numerical programming. This is a hobby project for me, so this is my way of learning it myself. And so from what I understand here, this is where we're performing in like an LU decomposition, and so we're calling into linear algebra libraries. So there's probably some external code being called here. But if we want to perform the same task using Clifford numbers, it takes about 3 nanoseconds on my hardware. This was taken on the same hardware. So this is really, really fast. And there's no allocations, there's no calling to get extra memory for this. And if we want to put this on equal footing, because we're getting a full solution set here, if we want to get that one particular solution that's closest to the origin, then we can get that by extending this formula a bit, but it still only takes about 1/10 of the time that it does. And I would not say that this is necessarily there's external factors affecting this, and I think this is a good point for anyone who might be working on static arrays, just to have a look at. That might be something a point of where it can be improved. But I do think that it's a really good case for showing like why you might want to use this package is that everything is implemented in Julia. There's no external libraries being called. It's very fast as is. Thank you, generated functions. That's where all the magic happens. Let's talk about another case where you might find Clifford algebra or geometric algebra to be useful. So you might have heard of of different types of filtrations used in topological data analysis. So let's say we have a point cloud. Each of these seem to have like a different structure to it, but how do we quantify that different structure? One tool we can use is to build disks around each point and seeing whether the disks overlap. So we see that we create a set of nodes here, or a set of edges, but also connections between edges. The edges are created when 2 circles overlap, and the triangles are created when 3 circles overlap. And that's a simplicial complex, and these come up quite a lot in topological data analysis. If we extend this to our other points cloud, we find a surprisingly different structure here. And with the construction of the simplicial complex, we can actually extract some information from this using the Euler characteristic or Betty numbers to get a picture of what's actually happening in these particular cases, or perhaps find common ground between disparate sets of data that may not be easily comparable directly. So performing this task, there are already libraries to doing this, but I think one of the really nice things you can do with Clifford numbers is actually solve some of these problems by using conformal geometric algebra to represent circles and finding where they intersect. Because it can be hard to tell. You can't just take each point and just look at their distances pairwise to tell if all 3 circles overlap. This is a case where this is not happening. Even though each pair of circles intersects, the 3 circles have no mutual intersection, and so in this case, we should connect them with edges, but not a triangular face. So we can use this to our CGA to actually find a solution to this problem. As an illustration of this, I can show you 3 different cases here. First is just some points that are clearly grouped together. They obviously overlap. We should easily be able to tell that this is a set of points that should be connected. All 3 of them as a face. There's also the near miss case that we showed that I think is worth talking about. And then there's a case of points that are nearly collinear, but they do overlap with each other. In the first case, this is relatively easy to rule out if we can construct a circumcircle, because if we could just find the circle that passes through all 3 of these points, its radius is much smaller than that of the filtration radius, or the radii of the circles that we're constructing around them. And so any case where your circumcircle has a smaller radius than the filtration radius, you can just say, yes, these 3 points are connected. But that doesn't work in the other 2 cases necessarily, or at least not consistently. This is true in the case of our near miss. The radius is slightly larger. It's not enough for us to be able to easily see this here. But in these three sets of points that we should draw a triangular face between. Drawing the circumcircle is actually not. You can't just do that. The trick here is that you need to find the most distant pair of points. So you do need to compare these pointwise, and then find in these cases you want to see whether the other point lies outside of this new circle we construct, whose diameter is the longest distance between points. And so that's easy enough to construct. But constructing a circumcircle might be a little harder, unless you're using CGA, in which case it's actually really easy to do. So in 2D CGA, we end up getting a couple of points that are, or we can define a point that is this particular equation where you have your coefficients, and then you have these extra two basis vectors, n naught and n infinity, which have this property of squaring to 0, but their product with themselves are, or the dot product of n0 with n infinity is actually -1. And the way that we construct these points is so that when we square them, we get the size, and the size of a point is 0. And we can do this in Clifford numbers, so this is one case where we need to just make sure that we are actually using the correct terminology here. These basis vectors are not defined to be orthogonal to each other necessarily, so the way I would work with them is defining constants that represent these vectors. I will include macros in this package in the near future to do this automatically for you, or handle the cases where you have a non-diagonal metric. And then you can just define your a point using this, and you can square the point to see that it is, of course, equal to 0. Now, in the case where you have 2 points, you can join them. And this join can be done with our wedge product. And we can square, we can't necessarily square this term itself. We have to divide it by this other term, and I use negative exponentiation just because I do want to be clear about what side you divide things on. This is not a commutative algebra. But using this form where you take the left contraction with the n infinity vector, and that's just a generalization of a dot product to any number of dimensions you want. It kind of generalizes the idea of projecting. Then you can define a radius, actually. You get half the length. Now, this part is something that you could do just by simple subtraction and squaring, as you would do with any Euclidean, squared Euclidean distance. But what you can do in a conformal algebra is you can construct this whole, actually it's still there. The circle defined by the 3 points, or they pass through all 3 points relatively easily with the with this particular with this algebra. You can also find the center of the circle if you need to by multiplying by the inverse of the pseudoscalar. And it also handles the case of collinear points very well, because in that case you would have a circle, but its radius is infinity. And this actually corresponds to the idea of performing a wedge product with this n infinity vector, because that actually represents a point that's infinitely far away. And it handles that just like projective geometric algebra without having to deal with exceptions or with unexpected values that may need their own special handling. Now, I'm short on time here, but the one thing I do want to address is that this is not the only package that does geometric algebra. There are many, many others. Just search through GitHub. But the reason why I registered this package is because I aim for the idea of allowing this to be highly composable and focusing towards ease of use. And so with that in mind, my idea is that any package that just works with numbers should be able to be generalized to Clifford algebras. And the way that I do this is by, instead of subtyping a vector type or an array type, these are actually number types. And this subtype relationship it makes more sense because other complex numbers end up being, or other hypercomplex number types end up being a subtype under a number. So this just extends that. In fact, you get a quaternion implementation. Awesome, yeah, and I know.
Yep. Out of time, we don't have time, or we have time for questions as the next person comes up. We have time for one question, and then, okay. Mike running back, and
Yeah.
Robert, who's up next, start setting up.
So I was wondering, in your example of solving the linear system, I was wondering, like, why is it so fast? Is it because, like, it's a special case of solving a linear system, or is the compiler doing a lot of work?
I use generated functions quite heavily in the process, that's used to perform a lot of the multiplication tasks in the various products. So this is a particularly fast implementation that's specialized for every particular algebra that you have. So yeah, that's just like, I think there's room for specialization and making this as fast as you can by knowing the length of everything and exactly how this multiplication should happen. Cool. Awesome. Presenting that. Yeah, cool. Awesome. Yes, thank you so much.
Yeah, I'll give you 10 and 5 also.
Okay. Very cool. Thank you. I should have asked earlier when the signs were. Are those, and this might be up there, were those for 5 minutes for the total slot?
Yeah.
Or for,
Oh, sorry, should have clarified.
That's okay. Yeah.
Okay.
Thank you.
So our next talk is Julian Academia, textbooks, Stanford courses, and the future.
Cool. Thank you so much.
Go ahead.
Hi, everybody. So, whoops. Okay, cool. So today I'm going to talk about how we use Julia in academia, and I know Julia is, very familiar with the field, and it's sort of born out of academia. And what I want to talk about is how we've been using Julia to develop textbooks and publish textbooks, what we're doing with Julia in some more recent courses at Stanford University, and some ideas for the future and how Julia could be useful in academia and what things I think we have to consider when using Julia. So first I want to talk about who I am. So I am a recent PhD grad at Stanford. I just finished in June, and I've used Julia throughout my dissertation. I was previously at MIT Lincoln Laboratory, where I used Julia as a specification language for an aircraft collision avoidance system. This is a photo of me in JuliaCon 2015. So that's what 10 years in a PhD will do to you. And then more recently, I've been a textbook co-author and the head TA for a textbook on algorithms for safety validation and a course that follows this textbook, where the algorithms in the book are written in Julia. So I'm a longtime Julia user. I've been using it since 2013. As mentioned, I used it as a specification language and led the team at MIT Lincoln Laboratory, where we developed an aircraft collision avoidance system and wrote the spec in Julia. My entire master's thesis and PhD dissertation, those research components were written in Julia. And alongside just the standard research use, I've also enjoyed some recreational coding, as well as code golf. And for anyone who might get bored in this talk, you might be interested in a package I made a while ago called tetris.jl. It's written in one line of Julia code. That's not what I do in academia, but if you want to just type in using Tetris, you can play in your REPL pretty nicely. So what I do in academia is ways in which we can use Julia. Specifically, one way is in writing textbooks. So over the years, since 2019, my advisor has written 3 textbooks using Julia. The first is Algorithms for Optimization. The next is Algorithms for Decision Making. And then finally, the one I'm involved with is Algorithms for Validation. And all these use a LaTeX template that I will talk about. And if you're interested too in the content of these books, all of the PDFs, the full PDFs, are available for free at algorithmsbook.com, and these are published through MIT Press with an open license. There's also a JuliaCon talk from 2019 where one of the co-authors of the first textbook, Tim Wheeler, explains more detail how they created this framework to write textbooks using Julia. So as a little snippet on how we do it, we have integrated Julia in LaTeX using Python tech. So what you see here is a page from Algorithms for Validation, where we have some figures and we have some, say, Julia code like this. And what that actually looks like is in LaTeX, we have a combination of LaTeX with equations and references and all that nice stuff that we love about LaTeX, as well as integrated Julia code that can show algorithms in a concise way. And we can use those algorithms to generate plots. So what we know is what we're giving to the reader is exactly the same code that we actually generated those plots with or generated exercises and actually computed numbers with. And so the compiled PDF from this particular page of LaTeX code is shown here, where you can kind of see the one-to-one of some of the LaTeX math, the block of algorithm code, and so forth. So this is all an open source textbook template called Tufty Algorithms Book. So if you want to create your own textbook, or even what I've done in the past is actually use this for course notes. It's just a nice way to sort of write up course notes and integrate algorithms and Julia code. You can follow along to this repository. And what you might sort of notice for the keen eye is actually these slides are also done in a version of that LaTeX integration with Julia. So all of these slides are open sourced. It's a combination of Beamer and Python tech, and there's also a template that I forked and made called Julia Tufty Beamer. And the nice part about this is we can, I'll show an example next, is how we can integrate Julia directly into this content. So an example here is we can compute Julia code directly in the slide or the page that's compiled to PDF. So what I'll show next is actually run when I run compile for this LaTeX document. So here we have a Julia REPL where I'm using a signal temporal logic package that we developed for the textbook. We defined some vectors, tau, and some formula shown here. And you can see, in Julia, of course, you can use nice fancy Unicode. We can compute things in this particular package, like the robustness value. We can do this again for another formula, and then plot this. And this is all run, the result of that robustness, and 3 in the second robustness, -4 is all done at compile time, and then same with the plot. This is all done in Julia using the pgfplots.jl package with the code that I just showed you here. So this is really nice because it allows us to have sort of a testable textbook and testable slides. So when we're trying to present material to students, it's a way for us to be certain that the numbers we're showing are the actual numbers that the code is using. So what's the good about using Julia for textbooks? So it's concise, so that algorithms fit within a single page. We don't have to define, sort of some boilerplate code or things in the background. It's sort of what you see is what you get, and we can be, we can include types if we want to, or not for conciseness. Multiple dispatch makes it actually really easy for us to develop a common interface that's used throughout a textbook. So say if we have a function that falsifies a system using algorithm A and algorithm B, we can actually just define a falsify function that takes in a different type. So this allows students to understand, we don't have to have a long function name for every specific algorithm. This allows us to make use of multiple dispatch in a really clever way. Auto differentiation, as an example, is really nice in Julia because it allows us for clean algorithms that just work with other packages, which I'll show an example of how we use some other packages that just work out of the box. We have developed a lot of integrated tooling, as mentioned, to run and plot Julia code during PDF compilation. Of course, as you see here, we're big fans of Unicode support, which means that the math we're showing in the textbook right next to the algorithm matches one-to-one. So in terms of trying to teach the material, it's not a sort of mental translation from lambda as a character to lambda spelled out. And when you're reading code, you can actually see, oh, this is exactly the one-to-one. And because it's concise, you can almost get equations that and algorithms that are exactly as presented in LaTeX math. And also there's this seamless package integration. So I think the fact that Julia is at its core based on multiple dispatch allows you to not have to reinvent the wheel and not have to change your algorithms to add so much unnecessary code around it. You can integrate with packages like we've done to a lot of these packages like distributions and lazy sets and interval arithmetic that just simply work out of the box. And so as an example for a showcase, I'll show you within the textbook how we're using interval arithmetic.jl and lasysets.jl. So we've defined this algorithm here which is a natural inclusion function. And we have some kind of very simple functions, specifically the reachable function, which given some algorithm and a system, then we can see what is the reachable set given the interval of that system. And as an example, in these three particular sort of low-level functions, the exponential, square, and sine, you can see what the interval function looks like here. So we have an interval from 1 to 2. You can kind of see how that creates a set that tells you what is the output value of that particular function. What's really nice is because in Julia, and specifically in things like interval arithmetic, they've defined how these interval functions work over some interval, and how these low-level functions work over some interval. So when we have, say, a more complicated system like an inverted pendulum, here are the dynamics of the inverted pendulum, and you can see we're just really using things like operators and sine, and it's a very simple dynamics, but because these are all chained together and using things that interval arithmetic already implemented, then we can do things like actually get a reachable set for the dynamics of an inverted pendulum without much effort. And that's really good for us, especially in the textbook, because we want to have this balance of teaching a student the material, making it work, but also not having too much overhead code or back-end code that if they want to just copy-paste what they see in the textbook, it just works. And you don't have to have, oh, well, here's just sort of the tip of the iceberg just for your understanding, but no, here's actually something you can go implement yourself and play around with. Of course, with everything, we can't just say everything's good and great. There are some not so good. I think what my experience of writing the textbook and teaching the textbook, which I'll talk about next, one of the biggest pain points, and I think a lot of people in this room can resonate with this, is Julia can be somewhat new to sort of your average reader. So this requires people to learn Julia in the process. Myself, being a longtime Julia user, I found that the transition from, say, MATLAB or Python is very easy, especially when it's alongside math and alongside plots that help you really understand what the code is doing. I think that's a perfect opportunity to learn, but this has been a pain point for some students and some readers. Because of that, there are potentially obscure idioms within Julia that require you to sort of over-explain. Things like broadcasting, anonymous functions, and multiple dispatch are syntactical sugar that help us get algorithms to be concise and look like the math, but sometimes might come off as confusing to some readers. And lastly, what we have done a lot of work on, but there's still room for improvement, is the tooling involved in actually creating this. So this needed to be built out from scratch. We do use Python tech in order to integrate the Julia compilation, but this does require you to build out these tools yourselves. So next I want to talk about how we use Julia in the classroom. So a course that we offered this past winter in 2025, it's a grad level course that follows the textbook on algorithms for validation called Validation of Safety Critical Systems. It's cross-listed in Stanford in the Aero Astro department and computer science, where I'm from. And all of the lectures, if you're interested, are available online. Sydney Katz, who is the lead lecturer, as well as the co-author on the textbook, and an award-winning lecturer, have some fantastic lectures. I recommend you check these out on Stanford's YouTube channel. The lectures themselves use Julia in ways where we have interactive lectures. So when you're describing a concept sort of on a flat slide with a lot of math, it's one thing to have animations within those lectures, but it's another thing to pop open a Julia Pluto notebook and actually play around with values. And if students have questions, you can actually answer those questions with visualizations. And so there's a lot of heavy use of that in our lecture material. One thing that I took the lead on is how we do assignments. So I wanted to do everything in Julia because the textbook's in Julia, and I love Julia. And so we have assignments that are written in Julia for the students to use. And we wanted to balance out things where we have some core functionality code that the students don't have to worry about, can be updated automatically. It's its own package within our own registry for our lab, as well as Pluto assignments, which is sort of the front end. So these are the things that the students would pass in, and these are interactive notebooks that the students can have beautiful Markdown and LaTeX integration, so you can actually explain the concepts to the students while you have them write code within the notebooks. And so we have these interactive Pluto assignments that give students feedback instantly. And we've done a lot of work to build out these notebooks. And as mentioned, we separated sort of the assignment core code from the actual code that the students would use. The interactive nature allows students to play with these algorithms themselves. There's no hidden state like Jupyter, so this doesn't confuse students. If you save a cell, any other cell that's dependent will run, including test cases. The open source nature, though, does require us to provide some clever obfuscation of the code, especially the solution. So if we want to check their code against some solution, we had to do a lot of kind of clever hiding of code. I won't go into too detail, at least now on camera, for future students, but if you're interested in how I do that, come talk to me after. Metaprogramming is extremely useful in this context because it serves as a lightweight, kind of unobtrusive way to track and enforce student requirements. So as an example, if we have a student who needs to fill out an algorithm that can only, say, run 1,000 times because we want it to be an efficient algorithm, we want to make sure we can track how many times those are run without this huge kind of code structure around it. So we just have a simple macro and you fill out the body of the function. And as mentioned, what we do is we provide these local tests in the notebooks for students to actually get feedback right away. What's nice too is once they have their local tests that pass, like in this case, green means passing, orange means failing, or yellow, excuse me, so they get feedback right away, then they can actually upload these to Gradescope, which I'll talk about next, as a way to get graded that goes through our grading system. So the way we grade assignments is we use Gradescope. For those of you who aren't familiar, it's a platform for you to automatically grade coding assignments. You can have tests online and have a really nice kind of interface for you to grade classroom assignments. We can actually upload Julia autograders, and so I developed a lightweight package called gradescope.jl that allows you to manage dependencies for your packages and create these autograder zip files that you just upload. And then what students do is they just upload the pluto.jl, their Pluto Julia file itself, because it's source code. So they can just upload that, and we actually can strip out the necessary components and test their solutions. So there's a lot of really nice ways for you to turn what would be manual grading into auto grading. And so kind of wrapping up a little bit is what I see as the future use of Julia in academia, and I'm really interested to hear your own uses of it as well as your own ideas for the future. I think here we're teaching a grad level course on safety validation, but I find that even teaching things like fundamentals like probability and statistics in pure Julia would be an exceptional example because it doesn't require you to have a lot of complexity in what you're teaching. It's just, because it's so concise, it allows you to just get down to the point of what you're trying to show. Another future kind of change would be unifying curriculum across compounding courses. So say if you do teach probability and stats in Julia, then your machine learning courses or your decision-making courses can actually build on that. So the stuff you've used in the past, you can see, oh, this is actually useful for me to say I modeled some system. Now I can go validate that system in this next course because we've sort of had this interdepartmental agreement that what you're going to do is going to help the students in the future. The thing that I feel like is lacking and we've tried to do is build cohesive teaching materials using Pluto. There's a lot of really fantastic Pluto notebooks out there. I think there's, everyone sort of builds their own version of something. I know Pluto as a group of people have built some really nice teaching tools, but I think what we've done a lot for this class is kind of made those a little bit more accessible and tuned to our needs, which are really about like grading assignments and ensuring students don't fiddle with the code that they shouldn't fiddle with. So something that is a little bit more cohesive would be extremely useful. Another thing too, which is related, is how can we build general grading frameworks? So there's this idea that if the student has open source code and they have some requirements to hit, how do we ensure that we can grade them properly? And we've done a little bit of that work there, but I think there's still some room for improvement. And along the same lines of that sort of hiding the code from the students, I know there's a lot of work on compiling Julia to binaries. I think that would be useful in this context where we don't want to actually show the source code, at least in an easy way. And so anything there would help our use of Julia in academia. And then lastly, which is sort of a kind of teaser demo into a side project, is the idea of being able to write interactive research papers in Julia / Pluto. So a project that I've been working on very briefly asked the question of what if we could interact directly with code in a research paper, but still have the kind of beauty and the kind of cleanliness of an academic research paper. So I wrote together a very quick package called Pluto Papers, which I'll show in a second, where we can actually define our LaTeX within a Pluto document. And I'll quickly show that here. Okay, so the idea here is you have sort of a very streamlined Pluto notebook where you can do things like define some equations and then actually have plots that you can interact with. As an example, I have a paper that I wrote during my master's that I turned into a Pluto paper, where if you look under the hood here, you can see this is all just markdown. I think even more importantly, you can see things like how we do math, which is just a LaTeX string macro, and it just allows you to write math directly in here. So this is defined as sort of a lightweight way to go from Markdown and Julia into a kind of clean package. And one of the nice things too is if you want to change, say this is the NeurIPS paper style, we can change it to the Tufty style, which is what we use for textbooks, and it just is really a CSS change. But one other thing that I think is more useful to do something like this is when you have some algorithm or some equations that you want to allow students to understand or readers to understand. And so in this case, we have some optimization benchmark function that's defined by a mixture of Gaussians, and we can actually play with these parameters to see how each of these parameters affects this particular function in a way that is extremely fast. And you could also envision this being used to show results and the code that was actually used to generate those results. So it's a reproducibility kind of point as well. You can have things like tables that show the code and auto-populate those tables with the Julia code. I think there's the balance of you don't want to rerun it every time someone looks at the paper, but you can have ways to rerun it if you need to. But having it all sort of in one spot as a way for people to interact with your papers, I think would be a very useful thing for the community. So with that, I will take any questions. I'll put this up here. And yeah, thank you for listening.
Great. Let's have a round of applause for the speaker. Okay, and first question back here.
Yeah, very impressive talk. I'm coming from your last comment about papers and the whole issue of reproducibility, which I think is very important. I know in astronomy we're trying to move toward reproducibility, and it's very difficult. You know, the Python people just want to put everything in a Docker document and go that way. I prefer Julia because I think it's a lot simpler and easier. So I guess the issue is how do we progress with that? Or do you have any ideas on that?
Yeah, so I think where I'm coming from too is in, say, the textbook. So there's a lot of times when we recompile the textbook, we don't want a lot of like the random or stochastic algorithms to show different results. And if we have a plot that we think is really good for education, we want to seed that plot so we can reproduce things without changing the textbook every time we compile. So I think I've found it is extremely robust in terms of just setting the seed and making sure that if you have results that are across multiple seeds, that you just are very open about what seeds were run. I think in something like Pluto Papers, you could actually show the code and show that if you want to recreate the code or recreate the results, you could do so. So you have saved results, and then you have new results, and that would be a way for you to help with reproducibility. But in my experience, really just seeding has been kind of a breeze from the Julia perspective.
Okay.
So that's some really some beautiful and impressive stuff. I was wondering, do you make the case with students or with your colleagues why you should be teaching in Julia as opposed to something much more prominent like Python?
Yeah, absolutely. We've gotten this question a lot, and students coming in sort of have the, why do I have to do this type pushback. I think, first and foremost, my advisor is a big Julia fan, so I don't have to try to appease to him. But I think the good that I showed about it being concise, it's being close to math, I think that it's helpful in the long run for students to not have to learn two things at once. They're just learning the concept. And a lot of times for them, Julia is just a one-to-one from the math. I think from our perspective, we sort of made the case that it's really useful for textbooks, and it's sort of the same case that I made 10 years ago about how we use this as a specification language for collision avoidance system. It can fit on one page, it's easy to read, there's not a lot of fluff around it, it's kind of what you see is what you get. I think that case being made for textbooks is a nice transition into, oh, well, the textbook's in Julia, we're gonna teach this textbook, and it's useful for students to be able to just take those algorithms and implement them themselves. And so that, what we found, and as another example, is the Algorithms for Decision-Making book, which is the one right before this last one, also has a Stanford course, which I've TA'd before. And in that course, we've designed the assignments to be agnostic to any language, and you just have to output a specific CSV file type. I started in 2019, and the textbook was an older version that didn't have Julia, it just had algorithmic pseudocode. And there was a lot of Python, there was a lot of MATLAB, maybe 1 or 2% were using Julia. Once we actually published the textbook that had Julia in it, it's about a 50-50 split between Julia users for students and then the rest of the languages, a lot of Python. But what that tells us is, they see the benefit of, if the algorithms are in Julia, then it's easy for me to understand them and kind of implement them, because I don't have to translate it to another language. I can just implement it and try to understand right from the textbook. So that's kind of been our cheat code, is the textbook's in it, then the students sort of are required to learn. And from our experience, there's been early on pain points, but we try to have these smaller assignments that allow them to learn it in the process. And I'm actually developing a course at Stanford now called Advanced Julia, so it's much more of like a teaching grad level students how, more of the advanced features of Julia, so that they can come in and then be the ones to convince other people that, yes, this is actually a good use case for it.
Okay, time for one more question, and while we're doing that, speaker to start setting things up.
This might be a silly question, but I've found that when I'm writing, for example, documentation, and I have Julia within a Markdown file, the linting between Markdown and Julia in VS Code is what I'm using. It's not always easy to get like the autocomplete with the Julia syntax inside of another file. Do you have some tool for that? Do you just have to deal with not having autocomplete?
That's a good question. Autocomplete in terms of like Copilot, or autocomplete in just terms of like names within
just
the
like
files?
Syntax checking, like did I get the end to match my begin?
I see what you're saying. When we have integrated LaTeX and Julia code, I'll get back to you at exactly what package is doing this, but there is a package that does syntax highlighting and linting on the Julia components within the LaTeX file. So there is something that is doing that for us. We didn't create that though. Yeah.
Okay, great. Now we're on to our next speaker. This next talk is about jetreconstruction.jl. Okay. And also, if the next speaker can be sitting somewhere up here, these are 10-minute talks, so it goes by real quick, so minimizing transition time is great.
Yeah, I know. I've made it worse.
I think you want non-mirrored, and then
Yeah, or just switch it to mirrored, it'll be fine. Yeah, let's just do that. Thank you for the technical support. Yeah, so quick talk about jet reconstruction. And first of all, thanks to the many people who've contributed to this talk. And I think that's actually one of the big changes between the talk last year and the talk this year, is that we now have many more people contributing to the package. What are jets? Because I guess not all of you are high energy physicists. This is an event display from the Atlas experiment at the Large Hadron Collider. And essentially these two cones that you see here are jets where you have a high energy particle that comes out of the collision point, and then it breaks up into many, many pieces. And the goal of what we do in jet reconstruction is to attempt to reconstruct what the high energy origin particle is of all of these pieces. And that's really important actually for a lot of the things that we do in the physics that we're interested in at the LHC. Roughly what the algorithm is a sequential algorithm which takes these energy deposits that you can see on the right-hand side there, and it starts to merge them together until it finds what it considers to be a good solution for the way in which the energy is distributed. And there are various aspects to the metrics which are important, but basically you would continue this merging process until you reach a certain number of what you would call the origin jets, or you've merged all of the energy in one particular cone. This actually project started off in 2022 as a student project, just a kind of proof of concept. Can we do high energy physics algorithms in Julia? And we were so impressed with the results that we went ahead and we released the package about a year ago. So let me start by telling you about more physics goodness that we have inside the package since last year. Our initial algorithms were for proton-proton collisions. These are the kind of collisions that we get at CERN today, because that's what the LHC provides. And a next generation collider that we're imagining for particle physics would actually collide electrons and positrons. And this requires a different class of reconstruction algorithm for the jets. So we've implemented these E plus E minus jet reconstruction algorithms as well, and we're very happy with the results that Julia is basically 33% faster than our rival that's written in C++, which is called FastJet. So that's great. We can do the E plus E minus reconstruction, and we've also added support for what we would call the event data model, which is essentially the way in which these events are being produced. Here we took advantage of the fact that Julia allows package extensions. So normal use of the package, you don't need all of the extensions, but you want to read E plus E minus, it draws in everything that you need, which is really great. And we can actually reconstruct 24 kilohertz on a single CPU core, which is extremely fast. We're very happy with those results. We also have extended the analysis that you can do inside of the package, because the core reconstruction is actually only the start of the process. What we're really interested in many cases is what's called the substructure analysis, where what you might reconstruct is what's in this big ring here, but you're interested in the little pieces which are inside. And so we've started to add algorithms which will allow you to do this kind of substructure analysis. And also, as LHC events in particular have a lot of pollution into the main event, we started to implement algorithms which can remove a lot of the unwanted soft radiation as well. So lots of techniques to skim the jets and to filter them, and in particular we've implemented the soft killer algorithm now as well. In the last part of the talk, I wanted to turn to our experience with static compilation, some more sort of Julia-specific things. The use case here is that we would like to perhaps use this package inside the triggers of the LHC experiments. And there, it would be quite important to have a statically compiled version because the trigger is very latency sensitive and it can't afford any unexpected complications. So we've looked at both package compiler and JuliaC. I think I'll just more or less skip this slide, but basically to say that we've had a much better experience with JuliaC than package compiler is essentially what we would consider to be the future of the way in which you produce statically compiled objects from Julia. But having said that, it's not completely smooth sailing. We are looking at the results that we have here, and essentially the JuliaC version basically overlaps with the FastJet version, so we're no longer faster than the C++ version, whereas in the pure Julia version we are still a bit faster. We've essentially tracked this down to the fact that we have some extra copying overheads when we're passing the results back into C++. So we're at a good point, but yeah, it's not yet a completely convincing way of using the package. Compilation time is quite fast. In JuliaC, it's 120 seconds, and we get a 320 megabyte untrimmed library. We've not quite succeeded in trimming everything just yet. Package compiler is worse in runtime. It's about the same in terms of library sizes. Now, we have discovered definitely some gotchas with respect to the package. It turns out that data structures in Julia don't always map nicely into C. And because we have basically variable size chunks of data, we actually have to use variable size vectors, and they don't translate quite as well. The memory interface is definitely, there's a bit of friction there. It would be nice if we could just take a pre-allocated chunk of memory and fill it, but that's actually quite difficult because of the way that the package is constructed right now. Certainly, we've made some efforts to try and make the structures immutable. These were actually not too harmful on the Julia side to have these mutable, but on the C side, it definitely helps to make them immutable, so we've done that as well. We're scratching our head to think about exceptions because we can't trim the library and have exceptions as well, so we might have to change the way the error handling is done. And we've been battling away with trimming, and we fixed many of the problems that we had from our initial case. There's a backup slide on that. It's certainly quite a helpful exercise to go through. We discovered quite a lot of issues with type stability by looking at trimming, but we're not quite there yet in having addressed all of the problems that we have. And I think our conclusion is that if you want to write code that you anticipate using JuliaC for, you probably want to think about that very much as your use case from the outset rather than trying to add it post facto. Okay, running out of time, I wanted to mention one thing that we loved about Julia when we wrote this package initially was loop vectorization. Almost all of our speed boost over the C++ comes down to loop vectorization and using this turbo macro here. But because loop vectorization has a somewhat uncertain future, which makes us sad, we've been looking at alternatives for doing that. And it's quite difficult, and it's not making things easier for our code. So that kind of really aggressive, incredibly well-tuned Julia optimization we'd very much like to see continue. So coming to some conclusions, this is such a fast talk. The package is performing very well. We're improving the feature set driven by user requirements. We will actually have a 1.0 release very soon with a few API changes as well. We have new physics in the pipeline as well. Static compilation, I would say, is not quite production ready, but it's been a very interesting exercise to go through. And JuliaC is definitely the favored way of doing that in the future. And we'd love to have a new generic solution for our loop optimization problem.
Great. We have time for one question while the next speaker gets set up. Question? Or, okay. Yeah.
Thanks.
And you're getting a 5-minute and 1-minute warning. Time includes time for questions. So our next talk is on getting started with supercomputing, and you're good to go.
Okay. Hi everyone, my name is Jillian Lahosky. I am at PSC, Pittsburgh Supercomputing Center. We are a part of the Mellon College of Science at Carnegie Mellon. I am going to talk today a little bit about our flagship machine, Bridges 2, as well as the Access program. Keep in mind when I say program, I mean project funded by the NSF. It's not a computational program, which is a project that allows all eligible researchers to get time on supercomputing clusters around the country for free. So to actually get started, let's talk about why you would even want to use a supercomputer. We're going to go pretty introductory for this. So using a supercomputer is really beneficial because much like Julia is a programming language designed to be optimized for scientific use, supercomputers are pretty much computers that are designed to be used in scientific research. Jobs are ran using a scheduler in Q. I was first introduced to supercomputing when I was working on a project studying quantum chaos. We were doing some linear programming, and it just took forever to run on my personal machine. It would get interrupted, I'd be running for 6 hours, and then I would have to do homework and something would break. So I would send that code off to our local cluster, and it would run for the 8 hours, be all safe and protected, and then I could just get the results. You also can use multiple threads, which gives you faster performance. That's essentially when you take a big task and split it up into a separate subtasks that are all performed at the same time. That can really increase performance, and parallelization is actually native to Julia. If you're using a lot of other languages, you have to use different packages that can just be a really big hassle to figure out how to work, get them all optimized and working. We also have CPU and GPU options available, which are just faster. And additionally, we have a shared file space. It's just controlled using easy Linux file permissions. So if you're working in collaboration with people, it's really easy for them to just hop on your project and go to your directories when something is needed, because you don't have to send it back and forth. Actually using a supercomputer is sort of just controlling it from your own computer. You aren't actually, at our data center typing in it or anything. So you're going to connect via SSH to submit jobs from your own computer. Additionally, we have a platform called Open On Demand. This is a more sort of IDE GUI interface if you're more comfortable using interfaces like that. We also have Julia 1.5.2 pre-installed on Bridges 2, but there are options to do your own install. We have pretty good documentation for this in our Bridges 2 user guide that explains the steps really clearly, so you're able to do your own install for whatever version or packages you need. I have an example of what a script would look like for how you would actually run your job. So down at the bottom, you see that line, Julia threads, Slurm CPUs per task. Essentially what that's doing is running a parallel job of whatever script.jl says. You would have this file saved in your directory on the computer and then use a command like sbatch, run it. It would get sent to wait in line until it's able to run, and then your job would run and you would get notified when it was completed. So if you're interested in actually using a supercomputer, it seems a little bit daunting, and I'm sure you think it's expensive, but it's actually not because of Access. So Access is a program funded by the National Science Foundation that I work on. What it does is essentially gives all of the different supercomputing centers across the country money to build these supercomputers, with the caveat that we allow researchers on to use them for free. So the way this process works is you aren't actually applying to use Bridges 2 or Delta at NCSA or whichever resource you may decide to use. You're first going to apply for your allocation within Access. You'll get awarded that, and then you exchange those Access credits that you receive to get service units on a resource, and then you're able to run your research, do your jobs, and do your science. The biggest issue when running into, or that I run into with new users who are requesting an allocation, is this different project types we have. So the Explore project type gives you 400,000 Access credits. All we need from that is an abstract and a PICV. If you submit your request for an Explore project after this, it'll probably be approved by the end of the day, and once you do your exchange, you can get on Bridges 2 in about 2 to 3 days. We also have the Discover and Accelerate options. Discover requires just a brief one-page main document telling us your goals as well as the resources you intend to use. And then Accelerate is a bit more extensive. We have a panel of outside reviewers do this, and graduate students are not eligible to be the leader of these projects. However, that is still an option. And then finally, we have our Maximize opportunities, which have 2 submission periods a year. We're in one right now. I expect the next one to open sometimes at the end of the year. Those are awarded only in service units. So you have to have a really good idea of what you want, what resources you're using, exact scaling of your code, and its performance. But that's something to consider if you expect to use a lot of computation. So who's actually eligible for this program? So graduate students can only be PI on Explore and Discover projects. We don't allow undergraduate or high school students to be PI on any projects, but a lot of these rules are pretty flexible, and we have a way to get you on no matter what. If you just ask us, we'll figure something out for you because we want you to be able to do your science. There's no citizenship or geographical requirement, but the PI must be associated with a US-based institution. So let's say you're a Nigerian citizen, you're a PhD student at CMU, but you're at home in Nigeria for the summer, but you plan to come back. You're still able to use an allocation as long as you're associated with that US-based institution. We only allow 1 allocation without a supporting grant, so you kind of get like a freebie at first where you don't need to have any outside support. And as long as that allocation is active, you have to have a supporting grant for another allocation. So that would be any sort of outside NSF grants, NIH, any grants from the college, in order to get that second allocation. We also do allow industry and nonprofit work. However, we do have the expectation that you will publish and share your results with the community because Access supports open science. And we want to make sure that there's nothing proprietary, that everything you do is being shared. To go back a bit to Bridges 2, these are the different partitions we have for you to run on. Up top, I have the exchange rates written. I know it's a lot of text, so I tried to bold everything that we care about. But up top, you can see the exchange rates. So 1 core hour is 1 Access credit. So if you have an Explore allocation, that means you're able to have 400,000 core hours over the course of a year. We have 504 RM nodes that each have 64 cores, which to go back to the parallelization example, generally your personal machine only has about 8 cores on it, but as you can see here, we have a lot more than that, so you're able to parallelize your code a bit more. We also have the extreme memory, which is pretty similar to regular memory, but just with more RAM, and then we have our GPU partition. We recently got some H100 nodes, which have been very, very popular and very useful for a lot of people. So there's a lot to do with Bridges 2, and like I mentioned, there are also a lot of other supercomputers, high-performance computers across the country that you are able to use with Access. So as much as I love Bridges 2, there might be something that suits you a little bit better. And that's just about everything, a quick run-through of it. I have my email as well as the PSC email listed there. I'll be around if you have any questions. Let me know. Thank you.
Let's have a round of applause for the speaker, and we do have time for a couple questions. And can the next speaker start getting set up, please?
Thank you. My question is about Julia version 1.5.2. Seems a little old. But Julia does designate certain versions to be long-term support or LTS versions. Would you consider a policy to always support the LTS versions?
Yeah, for sure. I mean, if we install our packages based on the demand we receive, because a lot of packages or softwares can be installed by the user using custom environments or different solutions. So for the ones that we have implemented, if we get enough requests for that, or if we just see a need for that, that's something that we definitely can look into further to keeping that on the machine.
Time for one more question, I think. Okay. And so our last talk pre-lunch is enhancing spectral dynamics and causal modeling with Julia. And
Yeah. So this is actually the first talk of the mini symposium on neuroscience in Julia. So because we had actually more talks, and I think I was bumped to this slot. What we did is we implemented spectral dynamic causal modeling in Julia. How many of you know what dynamic causal modeling is?
Nobody? Okay. So this is the tool that is most used, the most used tool in neuroscience, in imaging neuroscience. So if you do a functional MRI of the brain, and I'm just giving you actually an example, this is a mouse model, but this is the typical problem. So you take functional MRI. Functional MRI is essentially looking at blood flow in the brain, but that is related to neural activity. And what you would like to know, which parts of the brain talking to which part, right? What is the causal relationship between parts of the brain region? So this is actually a very interesting experiment. So this was published in Neuron in 2017. They combined optogenetics with functional MRI. And so what that means is that essentially you can put information into one part of the brain. It's a mouse brain. You can't do this in humans. But so you put a signal in there, and then you can see how the signal propagates to the circuit. It's a very, very cool experiment. Unfortunately, we can't do this in humans. But the general principle is that we would like to know from the data how these regions are interacting with each other, whether there's feedback, whether there's, all these questions. And after DCM was applied, these arrows here essentially indicating what is talking to what and in what way. Like, is it inhibitory, is it excitatory? That's essentially the start. So the way spectral DCM works, and by the way, this was developed by Carl Friston at the University College London. He's a big data analysis guy in neuroscience. This is used tremendously a lot. This is implemented in MATLAB. It's called SPM 25 or something like that. And the basic principle behind DCM is actually a state space model. So what you do is you essentially say that all the activity, the neural activity, is described by a dynamic differential equation. An ODE, it could be SDE. So this is essentially this term here, x dot. This is a vector, essentially, of all the brain regions. There is a function that describes the dynamics of the system, and there's some noise applied. And then you have a measurement, y, right, that is transformed from the axis, right? So for example, in fMRI, we know that the response of, if you see blood flow, right, then you can infer that the blood flow related to neural activity before that. And this is the convolution function from going from blood flow to neural activity. So you essentially have to do the inverse transform first, and then you have to start fitting your dynamic functions. So you essentially trying to solve the inverse problem, right? So you have a simulation. You wanna look at the parameters of your simulation given the data. And DCM has been around for a long time, and then it became very slow, right? Because if you take a lot of regions and you do this convolution, fitting this kind of inverse problem is very hard. So they came up with the idea of solving the inverse problem in Fourier space. If you think about it, if you have a convolution to your solution in Fourier space, it's just essentially a multiplication of the Fourier component, right? And so you can simplify the math. And what you do essentially is, rather than fitting the real data, what you're fitting is the cross-spectral densities, right? So you essentially take a time series and another time series, convolute those, take the Fourier transformation, that gives you the cross-spectral density. And typically, these also use Laplace approximation. Laplace approximation means that you assume that all the posterior probability distributions are Gaussians. So we implemented this in Julia because we are using it in our labs, but we also wanted to implement it with more flexibility. In MATLAB, you essentially have two models that you can choose from, linear models and this is called canonical microcircuit model that is more for electrode measurements in the brain. And you couldn't specify your own model. So what we did is we just went to Modeling Toolkit. Modeling Toolkit, you can essentially write any differential equation that you want. You take that, you assemble it into a bigger system, and then you define the parameters, and then combine this with the data, and you select a fitting method. So we actually have implemented variational Laplace approximation, but we're also using ADVI with Turing. So Turing has a very nice interface for it's not a Laplace transformation, but it's an approximate Bayesian approximate method to model the probability distributions. It's I think called auto differentiation variational inference. Okay, so I'll just give you an example of this. So this is a typical application of spectral DCM applied to the resting state network in the brain. So just to give you a sense of what that means is when you essentially try to think of nothing, your brain goes into a resting state mode. There's actually a series of nodes that will talk to each other and oscillate and do things, right, while you're not thinking. And this actually has become a major tool in neuroscience because what happens during resting state essentially reflects all the circuits talking to each other. So there's a lot of research done on in resting state making correlations between different brain regions. So this is an example where we essentially take the 4 major nodes in the resting state network and then apply DCM and get the weights. So essentially you can see that any blue arrow is a excitatory interaction, and any red is an inhibitory interaction. And you can see it can become very complicated. There's a lot of feedback and a lot of stuff going on. We also showed the ADVI method. We're actually right now trying to figure out why the ADVI gives sometimes quite different results. And that's actually surprising because these models are actually quite simple. Now I want to go actually testing spectral DCM against ground truth data. So we essentially did 2 simulations. We took a canonical microcircuit, which is a good model for local field potential. So if you put an electrode into your brain, that's what you expect the electric field to look like, what the voltage to look like. So we took 2 of those things, coupled them together with certain parameters, and then applied the fitting. And you can see that the cross-spectral densities are actually very nicely described by the fit. And then we also used an fMRI simulation, which is actually a linear model. So everything talks to each other in a linear fashion with noise. And so these are the fMRI simulations, and you can see that these cross-spectral densities are approximated pretty well, not perfectly, but pretty well. Now let's go to the speed comparison. This is always the thing about Julia. The comparison to MATLAB. Actually, my experience is that pretty much any dynamical system that I move from MATLAB to Julia, I get at least 5, 10, sometimes 60 times increase in speed. So here we implemented a spectral DCM in Julia MTK and added auto differentiation, right? So auto differentiation actually adds quite a bit of boost to the analysis. So you can here see that if you simulate canonical microcircuits, the speed increase is there, but it's not significant. But if you actually go to fMRI, linear neural mass models, when you increase the number of regions, then you see a tremendous increase from MATLAB. MATLAB is the blue curve, and then Julia MTK AD is actually the fastest. And then the other thing is we have some flexibility to actually modeling magnetic fields. This was not possible in SPM 25. So we can actually compare scanners at 7T and 3T and so on and actually model that. Conclusion is, so we have a DCM implementation in Julia. There's actually a paper coming out, I think, any day. So I got the proofs already. So this is published in Imaging Neuroscience. Should come out, I hope tomorrow. And this is with Carl Friston, actually. And it adds model flexibility. It improves the speed tremendously, especially for larger systems. And it's also implemented in the Norblocks GUI, so we have actually a graphical interface for that. So thank you so much. And if you have any questions.
Get a round of applause for our speaker, and it's lunch after this, so we have time for a couple questions.
Oh, okay.
But you'll be cutting into your lunchtime, so good luck.
Lunch, questions.
Looks like lunch wins.
Lunch, better lunch. Okay, okay. Bon appetit.
streaming and recording, so anything they say has to be through the mic or we will not hear it. Yeah, it just pops out. I just don't want it to roll away.
Hi.
Do you have any videos that have sound?
Yes.
All right, then we will connect both of these. And I'd like to test the sound too, if we could.
Yep.
Here's HDMI. I'm gonna open it first before we get logged in. Sometimes it won't take the audio over this.
Okay. All right, so we want to test the sound, I assume.
It's just unplugged into mine. Excellent. How are you looking for battery life also?
You know what, I can plug in, just
Okay,
to
yeah,
play
we
it
have
safe.
power right here in
Okay.
this box.
All
Just better safe. You look pretty good, but still.
Yeah. And I'm going to close down everything else.
Perfect. And I will literally just be at the table right back there. This is being streamed, so try to stand, as close to the microphone as you can whenever you're talking, or else they will not hear you on the. One other thing also, if you're connected to the Wi-Fi, you might want to put in Do Not Disturb just so you don't get any.
How do I do that?
It is up in the top menu, up right by the magnifying glass and the Siri button, right between them, those two little switch-looking things at the very tippy top.
Okay, so where do I do?
Very,
I'm just closing everything down.
no worries.
This is on. This is on. Okay, so you're saying
It's right between, yep, right there.
here?
Yep, and then Do Not Disturb is right here. They call it Focus now. You can just hit that and hit Do Not Disturb for an hour until this evening or whenever you'd like. All right,
Mm-hmm.
be all set now.
Okay, great, thanks. I'll plug in and then.
you ordered some glasses? Good.
It's actually maybe not so easy to see the screen. Yeah, yeah, very close. You know.
I think as long as you're centered, it's fine, but if you're sitting in those seats, it's really hard to see.
Before we start, actually, Andrew, you are actually a neuroscientist? Like what scale? EEG. And how about you?
What's the question?
What scale?
Okay, I think we're going to get started. So thank you for coming to our mini symposium on neuroscience in Julia. So we have several talks. So it's a little complicated because we have a talk now for half an hour, and then there's a keynote speaker, and then we reconvene for the neuroscience mini symposium at 3. And the first talk will be given by Lilian Mujica-Parodi on neuroblocks.jl. And we all had a workshop on neuroblocks yesterday.
Hello. So what I will be talking about actually is primarily the motivation and conceptual framework for what we're doing, because some of the later talks will get into more of the details. Okay. So obviously, this is a team effort. This is the NeuroBlocks team. On the top row are the co-founders. We have a spin-off, NeuroBlocks Inc. So NeuroBlocks is a software platform that is designed to support biomedical engineering applications. So from that perspective, it's optimized for, as you see, mechanistic integration of disorder and treatment relevant targets. So the format of it is very explicitly multi-scale. And the reason for that is because our motivation is the integration of these disorder and treatment relevant targets with actually the diagnostics that are at the top scale. So obviously the mechanisms behind the disorders as well as the treatments, mostly the pharmaceutical treatments, the targets are at the bottom scale. So here we have patch clamp, let's say local field potentials, EEG, fMRI, all the way to behavioral, the behavioral scale that is associated with the symptoms. But even though the targets are at this scale, the diagnostics, the measurements are at this scale, and the biomarkers are going to be at this scale. So that imposes certain specific challenges because we're going to need to develop a computational model that can operate at all of these scales and also is causal. So it's mechanistically integrated from the bottom to the top. So there have been, as some of you know, some computational modeling platforms that have tackled similar sorts of multi-scale modeling. Not so many. It's a hard nut to crack. But the first question that anyone working in this space has to address is, what is the scope of my model? And so there is the kind of the extreme view of detail, which is the best material model of a cat is another or preferably the same cat, which means that if we want to model the brain, we would literally need to model every single aspect of the brain. And there have been some approaches that tried to do this and computationally choked and were not able to get so far because this approach actually has some pretty significant weaknesses. And one of them is that it, beyond the computational elements of it, it also doesn't really know how to handle incomplete or unknown data. And so the approach we're going to be taking is the one espoused by my cat, Lemma, who takes the view that a computational model's level of resolution is a critical design choice that needs to match the system's goals. And so since our goals are that we have targets at the bottom scale and we have the biomarkers and diagnostics at the top scale, we're going to really focus on the structures, the architectures, the functional components that are going to link those components. But that we're not necessarily going to model everything. There are things that strategically we will be leaving out. Now, within the top scale, you know, what we have access to in humans, who are the individuals who are going to be getting these disorders, you know, we have neuroimaging paradigms, and within the neuroimaging world, you know, people often talk about networks, circuits, computational model. These are words that get tossed around, but in different fields and at different scales, these are used differently. So within the neuroimaging world, when people talk about circuits, what they really mean is networks, and what they mean by networks are correlations between time series that are acquired from different regions of the brain. What people often mean by computational, likewise, is not necessarily what a computational neuroscientist would view as computational. So if a neuroscientist at the clinical scale would think of circuits as essentially networks, a neuroimager often thinks of computational approaches as those that validate these networks across different data sets, different modalities. So they're really focused primarily on reproducibility, reliability and reproducibility approaches, as well as decoding functions. Now, the problem for our purposes, since after all what we're going to try to do is to toggle components at the bottom scale and then ask what are the emergent features at the top scale, the problem with both of these approaches is that both are discriminative, not generative, right? So they're not going to work in terms of simulations. And the ML approaches don't yield systems that are interpretable. So one of the presumed advantages of these ML approaches is they're very high dimensional, but the problem is, of course, that we're not going to be able to then identify what components are responsible for the outcomes. So connectivity does yield systems that are interpretable, but they don't really, that approach falls apart the moment we really start thinking about control circuits. And unfortunately, that's going to be a fatal flaw when we think about disorders, because what health is from the perspective of most of physiology is the maintenance of homeostasis in the face of chaotic inputs. And so dysregulation is really what happens during disease, and in order to model dysregulation, we have to think about control circuits. So here's an example of a kind of a canonical control circuit in physiology. So this is looking at glucose-insulin regulation. And one thing, you know, that's very obvious here is that there are different points of failure. So the same control circuit can fail in many different ways, and depending on how it will fail, it will give rise to different outcomes in terms of the measurement of the relevant components here. So glucose and insulin are being regulated, but the time series, the dynamics will look very different depending on how the circuit breaks. And those will give rise actually to clinical phenotypes that look quite distinct. So if you look at a type 1 and a type 2 diabetic who are untreated, they look like completely different diseases. And it's only if you really understand the mechanism, you understand that it's the same circuit that's involved, it's just dysregulated in different ways. And that provides a very good model for thinking about how psychiatric disorders can actually be implicating the same circuits and yet be dysregulated in different ways. And one of the important aspects of this approach, of course, is that once you have these generative control circuits, you can not just look at the timescales accessible to you during an actual experiment, but you can look at longer-term trajectories that look at adaptation or degeneration. And in the case of psychiatric disorders, this is really necessary. So certainly we know there are neurodegenerative disorders where we know that there's going to be a change that occurs over time. But in psychiatric disorders, that's the case as well. So you do have degenerative disorders like schizophrenia, and then you have, cyclic disorders like bipolar disorder and so forth. And so what we want to be able to do is probe concepts like hitting carrying capacity. So if there's a component of the circuit, so for example, if we want to actually assume that bipolar disorder is, the manic phases are associated by an over release or secretion of dopamine. So dopamine has precursors, of course, and if you're secreting a lot of dopamine, then you're going to deplete the precursors. You're going to hit the carrying capacity that will cause the system to collapse, right? And so it provides a mechanism for probing whether these overshoot and collapse type dynamics might be responsible for the manic and depressive episodes that you see, for example, in bipolar. And so the issue, of course, is that the standard approaches used in clinical neuroimaging that are dependent on correlations fall apart really the moment that you start incorporating feedback components, probably to this audience. I don't need to explain why. And instead, computational neuroscience relies primarily on ODE systems, which makes Julia really a wonderful environment to try to tackle this problem. And once we get into the world of ODE systems, of course, we can look at sensitivity to perturbation and control error and all of these concepts that turn out to be very important in the context of psychiatric disorders. So, again, not to belabor the point, but the idea here is that once we get into this world of control circuits, we have additional structure that goes beyond who's connected to whom and gets into questions of timing, thresholds, gating mechanisms, and so forth. And so we, at the fMRI scale, develop some of these approaches within a very practical context. So some of my earliest work was working with the US Navy SEALs, in developing a neurobiological diagnostic to be able to predict, using neuroimaging, how someone would respond to extreme fear. And so, if you're doing a study on predicting extreme fear, you have to induce fear. And so we found that one of the most reliable ways to do that was to have someone jump out of a plane at 13,000 feet. They had clothing embedded with biosensors. This is actually me. Because I was, I'm always like the first to test the equipment before we run the study. This is Duncan, one of our researchers. And so the idea here is that we are going to be able to take these initial measurements, look at how the brain circuits that regulate emotion are responding within this very controlled clinical environment, and then make predictions about how someone would respond to a very highly controlled, but also real-world stressor. And so that was a way to fine-tune these circuits and actually ensure that they were working. And what we found is that, that the circuit had, as with the type 2 diabetes, type 1 diabetes example, there are many different points of failure for how the circuit can break, and depending on how it breaks, actually that will position you somewhere on the spectrum between anxious to reckless and everything in between. Now, the problem with that circuit is that, we have these elements like these gating mechanisms, we have comparators and gains and so forth, which is, great if you're thinking from an electrical engineering standpoint, but the brain doesn't use filters and comparators and gains and so forth, and so the question is, if we want to give drugs, if we want to hit mechanistic targets, then those targets need to be able to interact with the bottom scale in ways that are biomimetic, right? So instead, we're going to have to ask, just as electrical engineering has its own computational primitives and capacitors, gains, and so forth, what are the computational primitives of brain circuits? So these are the microassemblies that I was referring to. So here's an example of a very small circuit called lateral inhibition. You have 4 excitatory inputs. The first that hits inhibits the rest. And depending on the tuning and how this is set up, this pattern is ubiquitous throughout the brain, but depending on how it's set up, it's going to give rise to different filtering mechanisms. So when we say that the brain is processing, these are the units, the sorts of units that are used to actually do that processing. So we can have a whole zoo of computational primitives, each one of which gives rise to a particular function. And from these microassemblies, we can then derive composite circuits. So we have these computational primitives. Those are the most fundamental blocks. From those, we can create the composite circuits. And then from the composite circuits, we can use those as building blocks from which we develop larger scale circuits. So that's the fundamental approach behind neuroblocks, which is we have circuits of circuits of circuits, or blocks of blocks of blocks. So here's an example. So here we are giving the neuroblocks brain. This is a simulation. Stimuli. So what's happening is it has to look at ambiguous stimuli and decide whether it's one thing versus another thing. So what it's doing is abstract category learning. And so it's going through these different steps. These are then validated across all scales. So this is going to be producing simulations which are then validated in macaque electrophysiology and then in human ultra-high field fMRI. So in macaque electrophysiology, we can validate in terms of the spiking neuron scale, local field potential scale, but also importantly, the behavioral scale. So the neuroblocks brain is actually learning. And so one of the very important aspects, of course, is this validation process. And one thing that is concerning, of course, is that in neuroscience, the threshold for validation is often far less than in fields such as physics. So typically in neuroscience, what we do is we take, an estimation data set and a validation data set that are essentially the same, right? So we divide up the data set, half is estimation, half is validation. And actually, if we're a little bit more rigorous, we will use totally independent estimation and validation data sets, but often of the same paradigm or the same population. But a far more rigorous way of validating a model is actually to develop a circuit or a model using, let's say, the literature. In this case, we actually extract information from the literature, integrate it, create these models, but not for any particular task, not for any particular population, then run simulations and make predictions and validate on a data set that had nothing to do with the initial data from which it was constructed. And in this way, actually, our model predicted new emergent behavior, which was then confirmed empirically in the macaque. So we actually discovered new neuroscience, which wasn't previously known. Hopefully this paper will be coming out soon. We discovered the existence of these incongruent neurons. So when the animal is about to make a wrong decision, actually there are neurons that fire selectively to this wrong decision. So obviously it makes sense that neurons would fire selectively to the right decision. Less makes sense why they would selectively respond to the wrong decision. We think this may be actually avoiding local minima by introducing some noise within the circuit. Lots of further questions you can ask, but the interesting thing is that the model was powerful enough to tell us something we didn't previously know. So in terms of pharma, obviously what we're going to do is have to start at the bottom scale. So here we start with ion channels and receptor binding. That's going to give rise to spiking neuron behavior. Those then input into these computational primitives. So if we give a drug that affects dopamine or serotonin or whatever, it's going to then affect the behavior of these basic processing units, and therefore it will affect the behavior of the circuit as a whole. So here's an example. So in this case, the neuroblocks brain is doing an oddball task. So what it's doing is the brain is responding to novelty. So it's learning a particular tone, and then the question is, how does the brain process what happens when it changes? And now what we're going to do is give the neuroblocks brain propofol. And so again, this gets developed from the field, from the literature, information about what is known about these computational primitives, about neuroanatomy and so forth, and then gets validated independently in the rhesus macaque. In addition, we have plug-in units for neuroblocks. So we have these neuroblock circuits. In addition to the pharma module, we can look at the impact of metabolism on neurotransmitter cycling. For example, this becomes important in lots of different disorders. So certainly in the context of brain aging and dementia, where hypometabolism is one of the key mechanisms, we want to be able to ask, how does learning, mechanistically, how does hypometabolism actually impact learning? And memory, but also there are other sorts of applications that are becoming more relevant recently. So many of you know GLP-1 agonists are very widely used now, initially for type 2 diabetes, then weight loss, but one of the unintended side effects is that they seem to have an impact on addiction, for example. And understanding the mechanisms by which GLP-1 agonists might interact with the circuits that are associated with addiction is only possible if you have a way to actually show the integration of these systems. We also have work on deep brain stimulation, which Herman will be talking about later in the afternoon. So in this case, we're working with a neurosurgical team at Massachusetts General Hospital. They implant electrodes in a particular location, and we want to use neuroblocks to be able to assist them with pre-surgical planning. Obviously, what we want to be able to do is not create these models by hand, but do a kind of an automated process. So I think one of the big directions that we've been hearing about in JuliaCon is SciML and the way to automate the creation of these circuits, and this is an approach that we're using also to use information to extract the circuits in an automated fashion. So that would include the circuit the composition, assembly, comparison, integration, and parameter estimation. The parameter estimation becomes particularly important when you're tuning a model. So in terms of the GUI, for those of you who are familiar with Simulink, or the talk that we heard first thing this morning, very much inspired by the tools that are used in electrical engineering. We are going to create circuits. We want to be able to run simulations, have a GUI that allows neuroscientists and clinicians to interact with the model in an intuitive way. In the case of Parkinson's disease, for example, I'm just giving one use case, it's very clear where you want to insert the electrode. But what, for example, if we have a patient with depression? So in this individual, we may have a 67-year-old female with depression, and the problem is that unlike with Parkinson's, where it's very clear where to place the electrode, in this case, there may be 6 or 7 different potential candidate locations for the electrode. And so the question is, how does the surgeon figure out where to put the electrode? And obviously, we don't want this person to just figure it out during surgery. So instead, we're going to do neuroimaging. We then extract individual-specific parameters for that patient, and then use them to populate the model, and then run simulations, putting the electrode at each of those different locations with different stimulation parameters. And then on the basis of that information, we can start to make decisions in an informed way about how to perform the surgery. So importantly, this is a multimodal platform, which means that we can consider the medications that this patient is on, as well as even the diet that she's on. So here's the GUI. So one of the big challenges in the very beginning is that circuits are, they're distributed throughout the brain. And so if you want to see the entire circuit at once, you can't just pick strategically for a particular slice. So what we've done is we've flattened the brain. So all regions of the brain, this is a human brain, doesn't quite look like a human brain because it's been flattened. But all the regions are represented here, and we've tried to maintain the spatial, geometry as much as possible. Yeah. And so here, what is happening is, you know, that you pick neurotransmitters, for example, you can affect receptor dynamics. In this case, once the circuit is built, you can then provide inputs. So the way it's constructed is inputs are on the left and outputs are on the right. So here, you can put inputs that are the deep brain stimulator, but you can also use inputs that are visual stimuli or auditory stimuli or whatever. So what you can do is in silico experimentation, you know, using the platform, that will make predictions, which then can be used to make decisions about how you conduct your experiment or your surgery or your treatment. So ultimately, what we want to do is provide a knowledge integration ecosystem, to provide a platform where lots of different information can be integrated in a principled way. So it's not simply, you know, taking a paper here and a paper here, but not having them be able to speak the same language. One of the advantages of using this blocks of blocks of blocks approach is that because we have, you know, these biomimetic computational primitives that are consistent throughout the brain. So you know, you have a set of these components from which you can derive circuits. The advantage is that all circuits can speak the same language, right? So different circuits will use different components, but different versions of the circuit, they have the same vocabulary and the same grammar. The advantage of that, of course, is that you can then facilitate the integration of circuits, the comparison of circuits, and then you can start to do you know, community-based modeling, where some people are contributing data, other people are contributing different models. You can then automate the comparison of the models with the data and then decide which models, you know, need to rise up in the hierarchy in terms of reproducibility and which models need to be discarded. And for all of this, you know, it was a natural choice to work with Julia because the ODE solvers are probably the best in the field, because the speed was necessary when you're doing multi-scale modeling. It's very computationally expensive, so a lot of the work that we've been doing is thinking through high-performance computing elements. And because there's a very strong community of people who are thinking along these same lines, using many of the same tools like SciML and lots of different applications. And so it was very much a natural choice. So I just should mention, if you're interested in learning more, you know, the commercial website is neuroblocks.ai. If you want to find out more about the research, you can go to lcneuro.org, and we are hiring. Thank you.
Hello? Hi, thank you for the talk. I'm thinking about your point early in the talk about choosing the right level of abstraction and thinking about how that relates to the neuroblocks. Like, where are the ways that that has been challenging with the system, I guess, is a part of the question. And then, like, the other piece is, you know, how do you enable flexibility in neuroblocks so that you can adapt the level of abstraction if you need to for problem, or what does that look like?
So one of the primary design choices was in thinking about the whole notion of a computational primitive, right? And the idea is that we needed to build in right from the beginning the circuits that were the microassemblies that were going to be necessary in order to perform ultimately what turns into cognition. So if you don't have those elements, so for example, in other platforms where the focus has been more modeling things like seizures, you know, the focus has been EI balance, you know, and you have a million, you know, neural mass models, which are all identical, and where what you're tuning globally is the EI balance. So if what you're trying to generate is something like a seizure and global dynamics, that may be the right scale to address those sorts of issues. If you're interested in traveling waves, you know, you think about the problem from that perspective. But in our case, the problem was, you know, something like a sort of a first generation neural mass model will be totally inadequate in thinking through disorders and pharmacological applications, because those disorders and pharmacological applications go beyond glutamate and GABA, right? I mean, most psychiatric disorders and their treatments are implicating things like dopamine and serotonin and acetylcholine. And so we needed a way, a mechanism that had enough structure at the bottom to be able to accept those targets. At the same time, you know, when I use the example of being able to model seizures, so if what you're interested in clinically are outputs that look like seizures, then your top scale can look like oscillations. But if what you're trying to do is to model psychiatric disorders and dementia, then the symptoms that you care about are cognitive, mood, and behavioral. And unless you are eliciting functions at the top scale that address those three components, you know, you haven't done your job. And so those constraints are ultimately what gave rise to a lot of other design decisions.
By the way, we will address some of this also in the next talk, where we talk about next generation neural mass models, which actually have this feature, right? So they connect microscopic parameters of neurons to global average behavior. And we're super excited about this development.
So one of the challenges computationally is that once you are dealing, like, so if you know that you need spiking neuron stuff happening at the bottom scale with enough specificity to accept these targets, and you need the clinical stuff at the top scale, that's a lot of simulation, right? And so what you want to do is to flatten the circuit at various key parts where you're incorporating a lot of that mechanistic specificity from the bottom scale, the spiking neuron scale, but without simulating it always from the bottom scale. And so those are called next generation neural mass models. And then the question is, how do you derive those? You know, like you need to have a large repository of next generation neural mass models, and they need to be adapted to different circumstances. And so the SciML approaches that we're working on are a way to automate the generation of those. Okay, thank you.
Okay, so let's thank the speaker.
Because this talk will address exactly what we were asking.
You'll see through the talk. It's much more of the predictive correlative model. Certainly, do you have any videos that have sound?
Okay. We are streaming and recording, so if anyone wants to ask any questions.
Yeah, no, I know.
So,
Because it's, huh? So in 2 minutes we'll get started. Okay. Mason, for example, should show up. Okay, I think, yeah, I think why don't we get started? So this is the third section of the neuroscience in Julia mini symposium. So it was kind of split up. So what I'm going to actually do is I'm going to address actually a question that was asked about how to flatten neural circuits. So in the brain, we have about 10 to the 11 neurons. I think the Blue Brain project that was lasted 10 years, I think, and was like funded by several $1 billion or 7 billion euros. They, at the end of the Blue Brain project, they were able to simulate 300,000 neurons. I mean, biological neurons, really nice neurons, but that shows you how difficult it will be to actually simulate a brain. I mean, even with Moore's law continuing, and I don't believe in quantum computers. It will just not happen. So the only way to do it, to achieving a good simulation of brain activity, brain circuits, will be that we will have mean field models of behavior, of neural behavior. So can we describe essentially a collection of neurons in average behavior. And this is where actually next generation neural mass models come in. And we actually, what I'm going to do is I'm going to, you'll see this is actually a very nice picture of the multi-scale behavior of a brain or multi-scale structure of a brain. You have cells, right? You have, and these cells, they have ion channels, and then you have connections between neurons, and you have brain regions, and on the top scale is behavior, right? So, you know, my brain is working, and I pick up my phone, and that's behavior. If you think about neurological diseases, then I feel depressed, right? I mean, how do you? Our brain should express depression or happiness or sadness or fear, right, and so on. And that's the challenge that we have. What we essentially do is we're looking to physics, right? Physics is very good at creating models that describe the average behavior. Right? These are called these are what are they called? Mean field models, right? Mean field models, right? And so what over the last few years actually, so I think it's about 5 or 6 years ago, some of the groups in physics actually developed what is called next generation neural mass models. And these models are actually, if you take neurons, and these could be just quadratic integrating fire neurons or Izikevich neurons. There's actually two next generation neural mass, actually 3 next generation neural mass models that have been fully developed. But the first one was QUIF. So you take a neuron and you take 1,000 or 10,000 of those, you connect them all to all, and you see behavior. You see emerging behavior, you see synchronicity. You actually see that these things oscillate as a function of time. And so the next generation neural mass models are a proper treatment of the mean field equations. So these next generation neural mass models, they actually they show exactly the same as a bunch of neurons connected together. And there's some assumptions for the derivation. The derivation is actually not so hard. There's no Fokker-Planck equation necessary to solve these things. And so I can just show you an example here. This is a next generation neural mass model derivation sketch. So you take a QUIF neuron, and then you essentially develop a way of giving you a firing rate and an average voltage. And then you also need a synaptic current and a recovery rate, right? So essentially, no, actually, these are only 2 equations. For the QUIF state, there's only two equations. For the Izikevich neuron, you get 4 states, essentially. So the QUIF neurons only have a firing rate and an average voltage. But what you can also do is you can couple the excitatory and inhibitory neurons together and have this coupled neural mass model, essentially. And the beauty of these things is that they will behave exactly like a simulation of these neurons, right? So that means that all the microscopic parameters that are in the neuron will propagate through into the neural mass model. Whereas old, standard neural mass models, they're just, equations that people came up with to describe the dynamics of the system, but they're not actually coupled to microscopic equations. So the only problem with next generation neural mass models is that the theory only works for fully connected neurons, right? And people have been struggling for years about this, but the brain is not fully connected, so what do we do, right? And years go by and theoretical physicists, argue about this and that, and they actually never came up with a solution, and we thought, why don't we just do something radical and, don't actually develop a real model, but let's see whether we can guess what sparsity or sparse connections would do. And for that we needed to actually, so here you can actually see different brain regions have different sparsity. So the hippocampus, the subcortical regions have the highest connectivity, and then anything in between is like 50%, and then the cortex about 5%. And by the way, 5% of all possible connections, right? So it's not like 5%. Yeah, sometimes people say, one neuron connects on average to 1,000 neurons, or every neuron has 1,000 connections, or 10,000 connections, right? Here, what we're talking about is the sparsity in terms of the percent of all possible connections, right? And so, what are we going to do about that? Well, we are looking for missing physics. We're looking for missing information in our differential equations. The other thing is these systems are chaotic. That's the problem. And chaotic systems are very hard to learn from. And we also need a method where we can learn from noisy observations, because we would also like to use this method from actually empirical data, right? So if we had a brain electrode, right, we would like to know what kind of model do I have to use for the brain. It has to be generalizable. So here is the method of universal differential equations. So this is a example. So let's say I have foxes, right? And I know about foxes that if I leave foxes alone in the forest, no food, they will die exponentially, right? They would just die. If you take rabbits and put them in the wild with no predators, they will exponentially grow, right? That's all I know, let's say. Right? That's all I know about the system. Now, if I put them together and measure, right, populations of foxes and rabbits, and this is actually a Lotka-Volterra equation, you will see that as the foxes go down, the rabbits go up, right? As the foxes go up, the rabbits go down. Because foxes eat rabbits, right? And rabbits, they just, and if there are not enough rabbits, then there will not be foxes, right? And so there's an oscillatory behavior which is seen all over ecology. Okay, so what do we do here? Let's say we don't know how they interact with each other, right? And what we can do is we can just plug a neural net into the differential equation, right? And pretend that this is just part of the differential equation, we can actually solve it, right? These are, by the way, neural nets that have only maybe 280 parameters. These are really small neural networks. And then what we do is we just teach the neural network data, right? So we feed the data in, we look for the minimum error, right? And then after training, the neural network knows exactly what it is. Then we interrogate the neural network with symbolic regression. So we take the neural network, we interrogate it and say, what equation is best described? What kind of symbolic, terms could I use to describe this neural network? And then these are standard methods. There's actually SINDI, which is more linear algebra based, and then there's also a genetic algorithm. This is actually symbolic regression.jl. By the way, this is one of the few packages. If you run the Python, PySR, it actually calls it Julia. There's often you have packages in Julia where the Python is called, but this is actually where the Julia code is called. Okay, it's a very, very cool package by Miles Cramner. So now the question is, why do we use UDEs and symbolics, right? Why don't we just use symbolics directly on the data? And the problem is that symbolic regression is really struggling with large data sets, right? It chokes completely on large data sets, actually. And then often noise will destroy this method, right? So UDEs are much better at learning noisy data. So for example, here we train on the Rossler system, and then the symbolic regression completely fails to predict. Okay, so in general, UDEs struggle to fit chaotic dynamics also, by the way. So one of the things that you see, and this really has to do with the chaotic behavior, right? Like the trajectories that you're trying to follow, there's many different trajectories, but then they're also diverging. So finding the true trajectory, right, of your experiment is very, very hard. And so what we need to do is to develop a method that circumvents this chaotic behavior, right? And then actually I have to thank Chris Rakakis for this, because he suggested this method to us. So he actually has on his, I think one of the websites, IML websites, is this example, which is very telling. So let's say you have a pendulum. You have an equation for a pendulum. let's say you simulate the data as L is equal 1, right? And then you ask yourself, can I, from this data, predict L, right? And you can write down the loss function as a function of L. And the loss function looks like the blue curve. And think about it. If you were to start anywhere on this loss curve, any optimizer will never find the global minimum, because they will always get stuck, especially when you start at low L, right? Like finding a minimum and then going up in the loss function to find a minimum, you know. And you can imagine more complicated systems. This is just a very nice picture that shows the problem. And the solution is actually prediction error method. The prediction error method is actually a method that was developed, I think, in the 70s, but completely forgotten. I think somewhere in Finland or something like that. It was never used after a few papers were written. And so the idea is very simple. We modify the differential equation with essentially a correction term that has the data in it. So whenever the UDE or the differential equation deviates from the data, we kick it back. We just say, we give a little k, and whenever there's a deviation, we push the derivative in the right direction. Right? And this is called the prediction error method. So just give you a sense of what we are going to do. We're essentially going to go data, known constraints, then learn the dynamics, exactly like what I showed you with the UDE, generate equations, and then validate. By the way, we put this paper, we just finished actually this paper, this is on archive. We sent it out for publication, but we haven't. Actually, we were rejected for the first journal, but we'll send it to the next one, like always. Okay, so the first demonstration is with the Russell system. So these are the equations. So this is like 3 states. The nice thing about the Russell system is that there's not many nonlinearities in the system. There's only essentially one term with zx or something. And so what we do is we essentially do some simulations, and then we guess essentially the form of y. Right? So what's the definition of y? So we plug essentially a UDE or a neural net instead of y dot. And then we also add the prediction error method. What you can also see here is that if you don't have this prediction error method, then you essentially, the mean squared error goes up and then it becomes constant. And that has to do with chaotic systems, that they have an O of 1 deviation from any change in the parameter. So if you take a parameter, add a little 10th digit like something, after a while it will deviate by order 1. And that's the accumulation of order 1 error in this plot. So after learning, so you can see that the prediction error method learns really nicely. It gives a very, very small mean square error. You can see that the relative error is very small. Like once we then reconstruct it and then run it with the UDE, you can get very good approximation to the error. And this is, by the way, if you plot the loss landscape as a function of the parameter, right? You can see exactly this behavior. When the k is 0, then you have a very, very rugged loss function. And as you increase k, you see that it gets smoother and smoother, and at the end, you see essentially 1 minimum for the true value. And what essentially happens is that the prediction error method is essentially smoothing the landscape that the UDE has to learn. But it still maintains the chaotic nature of the system, because if you get to the right trajectory, right, this term that we introduced is 0. Right? So we actually, in the approximation of the best UDE, this term is 0, so therefore it's still chaotic. It may not be chaotic when it approaches there, but so we also just checked whether the k will affect the parameter actually, right? So because you can imagine if your k is too big, then the system will maybe reach the wrong parameter, but this is actually was not a problem. So you can actually look at the original landscape in 2D, like in A and B parameter, and see how this minimum changes as a function of k. This is actually, okay, so I missed, I think, one of the plots. So what we were plotting is actually the mean square error as a function of k. And you can actually see that at small k is essentially high, right? And then there's almost a sigmoidal fall off at a certain k, after which it works. So you have to find a large enough k for it to work. You shouldn't be too large because then you may not be chaotic at all. But this is kind of the tricky part of this method. But we have not found any system where we couldn't find a k to work with it. Okay, we also tried another system. This is the Pretzela-Pollock circuit. This is actually a nice circuit. It's an electronic circuit that actually shows chaotic behavior. You can build it at home on a breadboard, and it's really neat. And then we took one of the signals that as an output, and then we added 5 times as much noise, right? And we thought, like, can you train on this data, right? And indeed you can. So we essentially replaced y, then we checked against the measured noisy error, and this is the original attractor, and this is the noisy attractor. So it looks perfectly the same. And it also gives us the right equations, right? So it gives the perfectly correct equation. You can test it also with symbolic regression, and symbolic regression gets it completely wrong. Like, wronger than wrong. It's absolutely wrong. So that's a good sign that our method, actually, our procedure works. Okay, now we want to come to the crucial part for neuroscience. So I told you, right? We have this is actually the Izikevich next generation neural mass model, which I think is very important, very interesting, because the Izikevich model is a simple model, but it has all the features of neurons, right? So all the features, all the behaviors like frequently firing or bursty firing or not firing, all of these things you can, and there's actually papers that show in each brain region you can find the parameters for the neurons that are in the thalamus or whatever, right? I mean, wherever you are, you can actually find the parameter values, which sort of tells us that we can, these are microscopic parameters that we can then change. So this is a very good model to try it. So this has 4 states, and then what we did is we simulated, I think it was about 1,000 Izikevich neurons, we simulated at different sparsities. So we did 100% sparsity. That's actually the 100% sparsity result. That's the one that the next generation of neural mass models predict. And then we just reduce sparsity. We scaled the connection strength a little bit because you want to have an average synaptic current that goes into a cell. But you can see that the frequency changes and the amplitude changes of these systems, right? And actually, there's two things, right? So the frequency, but then also the synchronicity changes. So if you think about it, why is the average voltage going up and down? It's because there's a synchronous behavior. The neurons behave as if they're all firing together, and then they're also not firing together, right? That's an emergent property of this assembly of neurons. And when you reduce the sparsity, the synchronicity goes down, and also it goes faster, right? And so what you can actually do is, so this is the frequency plot. So what you can do is essentially, it fully connected is around in the gamma range, and then as you decrease the sparsity, you get essentially the alpha range. And that's pretty much exactly what you would see. Like the subcorticals typically, they're slower oscillating than the cortex, right? That's exactly what you do. And then we also looked at synchronicity, right? So if you, now this is the frequency plot. Increased sparsity and decreased synchronicity. And then we actually went into a data set where they have LFP data of different brain regions and looked at synchronicity, and you see exactly what we predict with the sparsity. That the sparsity is lowest in the cortex, right? And then kind of in between in the prefrontal cortex, and then in the medial, I can actually read this. So exactly what one will predict, right? So that's pretty fascinating. Okay, so I want to summarize. So we have created essentially a method that can learn missing physics and still exhibit chaotic behavior, which was not possible before, even actually handle noisy data. So the PMUDD is actually a generalizable model, right? So you can use this for anything, right? So we're actually thinking about if you, let's say, have a brain region that you don't know at all, right? But you have data on it, then you can use this method essentially to create a next generation neural mass model, right? To create essentially this set of differential equations that would best describe this. And so what's next? Essentially, what we're trying to do is to go into more complicated neurons, right? So we would like to do this with Hodgkin-Huxley neurons because they really have microscopic parameters that we're interested in, because then you have ion channels. We also would like to move into receptor dynamics, right? Because that's what drives diseases. That's where medications act. And it's very important to essentially have models where you don't have to simulate hundreds of thousands of neurons, and at the same time you have the microscopic knobs that you can turn. So it's pretty obvious. Okay, acknowledgements. So this work was really done by Anthony Chesborough. He's a MD PhD. He was actually supposed to give this talk, but he is a doctor, right? And he has actually rotation, and he's probably holding babies or something, or dropping babies. He's in surgery, right? He's in surgery, which is even harder to get away from. And so then David Hoffman, he worked actually for Neuroblocks for a while. Waybav Dixit, he's at MIT. He's a master's student at MIT. Earl Miller, he's a neuroscientist at MIT. Richard Granger is at Dartmouth, he's also a neuroscientist. Alan Edelman, you all know him. Christopher Caucus, he was really important in the sense that he had like this idea, said like, oh, there's this technique, that has long been forgotten. Why don't we apply this to the chaotic system? And Lilian Mojica Parodi. So I also want to acknowledge the Laufer Center. Stony Brook has paid for this. There's also, I think, a program. The Anthony Chesborough is part of the. He's an MD PhD, and so there's a NIH program that funds MD PhD programs. And then we are very grateful to the Buzicki Foundation, Brain Research Foundation, for funding this work. And with that, I'll take a few questions. Yes. Oh, yeah, we need to use a microphone because it's not only live streamed but also recorded. And
yeah, thank you for the talk. I guess one question I have is, have you thought at all, like one simplification the model is making is, at least as you presented, is that the type of sparsity doesn't matter, that there's just sort of sparsity, not sparse on this end and a lot of sparsity on that end. And have you thought at all about like heterogeneity in the sparsity and what that would look like for this model?
Yes, so you're absolutely right. So what we did is essentially we took the simplest approach. For us, 1,000 neurons, then you randomly connect them to other neurons in a certain way. By the way, we don't do it completely randomly. When we set a density, we say that on average, every neuron receives a certain number of connections. So because if you do it really randomly, then you have a neighborhood that doesn't talk to another neighborhood. That would be really bad. So we're already taking care of that. But you're absolutely right. There are structures where certain neurons are have different number of connections to other parts. This is all something that we have to now start, right? So we have to start characterizing all these different connectivities. It's on our list. It's it's definitely on our list because I mean, you had also suggested to simulate cortical columns. There's a lot of information about structure that we can incorporate into these models. If we know how the neurons work, we can take care of the connectivity, and then we can take care of making next generation neural mass models. And the other nice thing about the flattening is that, for example, you saw the propofol, right? So we're actually thinking about how to do propofol. Propofol, each sound is handled by a different column, cortical column. So what we essentially would do is we would model each tone with its own chain of next generation neural mass models, and then for every behavior, for every other path, you can use a different one. So that's how you would probably flatten it. I mean, we will never be able to simulate the whole brain with this, but we can simulate the parts that matter, I think. That's the goal.
Thank you.
Okay. Any other question?
Any other question?
Yeah.
So with your example of using the PEM method, you notice you were adding like the K times the error term to just kind of one of the states. Is that kind of generally that you would add that error term to like the neural network term, kind of keep those together? Or can you have like the error term added to a different state?
I am not sure whether I understand. So, I mean, we can go back to the equation. So what are you worried about? Okay, so here. So we have a neural network, right?
Yeah.
And then we have a error prediction method.
So I think the question is, imagine your observations are on x dot instead of y dot.
Okay.
So can you put the error term on the first equation?
Yes. Yeah. No. So in general, I mean, okay. So here, the method, and we actually show this in the paper. So we show the general term. The k could be a vector, right? And so what you could do is if you have data of x, you just put another term, k term, on the x value, right? Because the thing that we did is we had only data for y, and we assumed that the x is exactly what we observe, right? So that's sort of like you only put the k term wherever you have data, right? And the other ones then just develop from the natural, the equation. So so maybe better explain. So we assumed the correct behavior for x, right? We assumed the correct behavior for z, and we pretended that we didn't know y, the term, but we had data for that. And you can, in principle, right? We have actually not tried this, but I think it can be done. If you had none of the information and then only data, right? So that's the question, whether you can do this. But in principle, it could also work.
So, but I guess to run the simulation, like the initial conditions of x and z, or the initial conditions kind of to start.
Oh, so you're talking about the initial conditions?
Yeah. Do you have to know those?
Yeah, so in this case, right, you're absolutely right. So we always use the same initial condition, right, as the simulation. It becomes more complicated, right? So if you have to guess the initial condition, then you have to draw it from the distribution. You have to model a distribution of the initial condition. But that has been done in pins. Pins do this all the time. This is just an extension. So this is the first time we show that this works. But I think initial conditions, so for example, if you've only data, right, then you're absolutely right. Like then it's important to estimate the proper initial condition, right? But I think it can also be done.
I don't think we have time for.
Okay. Okay. So then let's move.
Well, thank you again.
Okay.
Will be given by Mason Protter. Is this actually working? Oh, yeah, okay. So this is on graph dynamics. I think I mentioned this in the workshop. I don't know whether everybody was at the workshop, but one of the things that we ran into is that modeling toolkit is just too slow for 100,000 neurons, let's say. And so Mason Protter has been working on this, on graph dynamics for a little while, more than a year, right? Like how long have you been?
Yeah, about a year and a half.
A year and a half. And he essentially created his own compiler, right, to compile dynamical systems. And he will tell us all about it.
Okay, so one thing is I'm just want to get my mouse cursor on both screens because I'm going to need that. Yeah, I'm going to have to switch to mirroring. Sorry about that. Oh, crap. No.
I don't have your laptop on the stream. I'm going to have to change your
Okay.
device settings real quick.
Okay.
James, I don't have an option for 59.9 on the refresh rate. I only have 48 and 60 hertz.
That shouldn't matter.
That was what was going in. Oh, you're right here. That was what was going in earlier.
It's more the resolution.
Okay. You want to run up there and tell me if you see it? Sorry.
No, it's fine.
You're not seeing it? All right. Hold on 1 second. This is a framework. Neither. It's neither a PC nor a Mac. I assume this is some kind of Linux.
Yeah, it's Linux.
Yeah, it's Linux.
So some output display adapters will scale down
Okay.
resolution, but keep it the same.
I see.
If that makes sense.
Yes. Okay. So.
So I don't know if there's a way. I'm not familiar with Linux machines.
Okay.
I know in Windows there's a way to tweak the display option so that it is both displaying and outputting the actual resolution.
Okay. So maybe if we turn off the scaling. Well, this is about he doesn't have for the live stream.
I don't have it on the live stream.
So, can I just quickly email you my slides and then plug your laptop in? Okay.
Yes, that would be great. Thank you. Sorry about that.
Yeah, it's fine.
Just gonna have to be quick.
Is this a PowerPoint slide?
Yeah.
Okay. Do you have PowerPoint on your MacBook? If not, okay.
Everything on the
Excellent. I know some just have Keynote.
whatever that means. Okay, I just have to find my email.
Or I'll send it to you on Slack.
On Slack. Okay.
my screen's tiny, so I can't see anything.
That's okay.
You have to speak faster now.
Yeah. Sorry. I left a bit of slack, so it should hopefully be okay.
Okay, so we just run it.
Oh, okay. Okay. So, yeah, we've already kind of heard about neural blocks a couple times, so I'll skip over that. And basically, one of the core building blocks of our neural block software for neurodynamic simulations is we're originally using a lot of modeling toolkit. So basically, what we do in neural blocks is we build these structures that represent different building blocks of the brain. So it might be a neuron model, it might be a neural mass model, whatever. And it has information about parameters, states, equations, callbacks, stuff like that that might happen during the execution of the model. And then we store these things, we generate a graph of all these different objects representing how they interact and talk to each other. And then we pass these things into, we compose them all together with modeling toolkit, defining connection equations that say like, okay, so the junction variable of this LIF neuron is the sum of all the voltages of the neurons that it's connected to. And then what modeling toolkit does for us is it performs structural simplification, eliminating all these junction equations and replacing, say, this JCN with the sum of all these voltages in. And so this modeling toolkit is a very high performance system. It works very well for small systems, which is what it was designed for. So like, for instance, if I had 2 integrated fire neurons and I just wire them together like this, have them each talking to each other, modeling toolkit will generate a kernel tailor-made for this problem, for these equations. And don't worry about what this says, but we basically just have a big list of equations describing how the dynamics of this system evolve. However, if we start cranking up these numbers and say 10 integrated fire neurons coupled all to all, we end up with order 100 equations in here. And this is because modeling toolkit basically is just a very general system, and it's designed thinking you're going to have heterogeneous structure, and we just have to simplify it down as much as we can, and then write out those equations and pass them to Julia. So we get n-squared expressions here, but also Julia has an optimizing compiler. And optimizing compilers look for opportunities to fix things and make them faster, so it has to look at each pair of expressions. And so in general, you get n squared on top of that n squared. So you get n to the 4 in terms of the compilation effort you get with this. And every time you change anything, like the number of connections, the number of neurons, you have to recompile. So in practice, for a unrealistically dense system, so all-to-all coupled LAF neurons, we see something like n to the 4 scaling asymptotically once we get out to what I would call big systems for modeling toolkit, but in terms of neurobiology, very, very small. Like this is 160 neurons here, takes almost 2,000 seconds for a kind of end-to-end system where we compose all the blocks together, generate the system, do structural simplification, compile the system, and then solve it. So, that's what's being timed here, and it just starts exploding. We don't generally, now this wasn't such a big problem for us at NeuroBlocks, at least initially, because we don't generally care about these sorts of densely connected, soupy systems where you just have like lots of neurons talking to each other. We more care about these sort of structured models, like, for instance, this cortical striatal model that has been developed by some people in our lab, where you have kind of a very sparse cortex talking to a lot of control systems and stuff like this. But even this model, which is relatively big, it's but rather sparse. So it has 600 neurons and 6,000 connections. We start really running into some limitations that make us at least not want to make it bigger. So, for instance, the warm-up of this learning circuit is around 7,500 seconds. And if we want to do all these Hebbian learning trials where we show it an image and then it tries to categorize it and then we give it some simulated apple juice to tell it was good or bad if it got the answer right, that took around 40 hours. And a lot of that time was actually in compilation time due to the parameter changing around weights in the model. So these long compile times, I mean, kind of obvious. It slows down how long it takes us to develop models. If I make a typo somewhere in a thing and then I have to wait 7,500 seconds just for it to compile and run and then give me garbage output, that sucks. And it also just limits the sort of models we can study. So to that end, we've been developing graph dynamics. This is open source, and it's basically our modular framework for talking about clusters of interacting kind of enclosed systems that can send signals to each other and receive signals from each other. So instead of all the machinery and modeling toolkit where it might be trying to perform simplifications throughout a system, we know what variables need to be eliminated, and that's just these junction variables connecting neurons. But this is very general infrastructure. We think like this could be applicable for things like even PDEs or climate models or whatever, but we're applying it to neurobiology. And basically the key insight here is that we try and loop over repeated substructures and only do this sort of unrolling at the type level when you encounter systems that have different equations. So very roughly what this looks like is, say we have some system that has S and T type subsystems in it. We'll partition it by the type, so we take all the S type subsystems, put them into one bucket, so you know if you reach into this bucket, you're always going to get an S, and the compiler can make plans based on that, and all the T's go in their own bucket. And then we build up these connection matrices, which we also, okay, the formatting got screwed up, but basically these are sparse matrices describing the connections between each of these components. So, so we partition these based on the type of the connections. So in this thing, I've got the blue connection 1s, the orange connection 2s, and the green connection 3s. 3 sets of these partition connection matrices. And basically, so if you want to see S3 get a signal from S1, you would look somewhere in this connection matrix. If you want S5 to talk to T2, then you would look in this connection matrix, stuff like that. So we store this highly nested structure that tells us how all these systems are interacting with each other. And then basically the way we actually solve the differential equations is we unroll all these type level operations. So what that means is basically we tell it, okay, generate a loop, a dynamic loop over all the S's, where you say, okay, look at S1, and then for each of these outer matrix structures, then go into the innermost connection matrix and generate all the connections within the S's that go into S1. Feed that input to S1, go into all the connections from the S1s to the T2s, feed that in. And so on. And then we loop down here with a dynamic loop that doesn't scale at compile time, and then we do the same for the T's. And basically, we always are able to preserve type stability here at the cost of introducing some nesting. And basically, the advantage of this is that the amount of time you spend compiling is just eliminated. It doesn't matter if you're doing a 2x2 system or a 10,000 by 10,000 system. The compile time's the same. You're just talking about the runtime. So this is the same data I showed you before with that n to the 4 scaling, but I've put it on a log scale because otherwise you wouldn't be able to see this line, which is the time it takes graph dynamics to do the same system. So this is the end-to-end comparison. And that cortical striatal example I talked about, that construction warm-up time went down to 75 seconds. It's factor 100 improvement and a factor 10 improvement in the total learning structure. So that goes from waiting a couple work days to get some results to put something on in the morning and you can look at the result in the afternoon. And then it turns out that this green line here, this is also actually, there's a lot of overhead here, is mainly coming in the asymptotic case. That overhead is coming from walking through this graph of unstructured systems or potentially unstructured systems where it doesn't know what's in the graph, and then generating these type partitioned lists. And so if you have like a very homogeneous system, like say this big cluster of LAF neurons, you can actually provide your data to graph dynamics in a pre-partitioned form where you have all the connection matrices and the subsystems pre-partitioned, and then you can eliminate another couple orders of magnitude in overhead. So this lets us scale up to, I think I went to 40,000 by 40,000 densely connected LAF neurons, and I didn't go any further because my laptop ran out of RAM, just storing all the connection matrices. So depending on time, I'll give you a quick overview of how you can actually use graph dynamics in practice. So basically, you would start off by just defining some sort of struct that holds data about, that we'll use to basically represent like the initial state of your system before it gets passed into graph dynamics. So in this case, I'm going to take some LAF neuron. It needs a name. This is basically used for the symbolic indexing, so we can generate plots and stuff at the end. And then it stores a bunch of parameters of the system. You then pass this to the graphdynamics.toSubsystem function, which we overload. So we basically add a method to toSubsystem. And what we do here is we generate two objects, the subsystem states, and this tells graph dynamics that basically the V and the G variables are going to be dynamical states that have differential equations describing them. And then all these other things, C, EM, RM, blah, 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 these are all parameters of the system. And and then we kind of wire those together into a subsystem of states and parameters. And the reason for that is basically that differential equations.jl expects the states to be in their own vector of just like a dense vector that it can do linear algebra on and stuff. So we need to be able to quickly separate out and the states from the parameters and stick them back together. Then after that, there's this subsystem differential equation. So you have to tell graph dynamics what an input to a subsystem looks like. So this LAF neuron, for instance, just has a simple input that's the initialized accumulator of this input is basically just to say like, okay, if there's no connections, then it's just gonna receive JCN equals 0. And I put this as a name tuple so that we can kind of keep track of the names of these different variables. So then the subsystem differential function, we then add a method to that where it takes in a subsystem, an LAF subsystem, an input. So that input will be of this form, but the actual value might change, and the time. And then we just unpack whatever variables we want out of it. So in this case, we took out the states, the parameters, and the JCN variable, and we calculate the differential equation like this. And we return a subsystem states object that has the same structure as the original states. But in this case, each variable is going to be the derivatives of the variables. So we want to generate a subsystem states that has the derivative of V and the derivative of G. And then the only other, so there's a couple more steps. If we want more structure, we have to tell it how connections work. So you can make a connection struct. So for instance, this is a struct representing connections between neurons, and it just carries some weight associated with it. And then we tell it how this connection struct acts on two neurons. So there will be like a presynaptic neuron in this case and a postsynaptic neuron. And we just say that the junction voltage going from the presynaptic neuron to the postsynaptic neuron is just the weight times the voltage of the presynaptic neuron. And then we return this thing. And this return needs to be of the same structure as this, is the only kind of constraint there. Other than that, you can kind of do whatever you want. So then, last thing here before we run it, we want to define callback events, because LIF neurons, it's too simple a model to have dynamical resetting of the voltages. LIF works by defining a callback so that when the voltage of the subsystem exceeds some threshold, then we want to reset the voltage back to some resting potential. So we can do that by telling graph dynamics that LIF neurons have continuous events. We also support discrete events, and depending on the subsystem, it might make sense to use one or the other. Basically, the difference is that a discrete event, there's a condition that's checked at each time step, and then it just sees, is this condition satisfied? If so, apply the event. A continuous event has some condition that has to be met at a point. And so if the solver basically takes a big step and it sees that the voltage has spiked up past V threshold, then it takes a step backwards, and it will backstep until do root finding until it finds exactly the point where the voltage is equal to the threshold, and then apply this continuous event, which basically we pass it here a few arguments, the integrator, a view into the states, and a view into the params, so that we can modify the params and the states in place, and the subsystem originally. This subsystem is usually just used as a handle for dispatch. So basically what I'm doing here is I'm setting the voltage equal to this parameter E sub m, and I'm setting this conductance G equal to G plus this synaptic conductance. And then after that, you're free to start assembling and using these subsystems. So the easiest way to do this without the pre-partitioning is to define a graph system. And then you can basically define a bunch of these LIF structs and then add connections between them. So this add connection G between the source and the destination neuron with some connection variable here. This neuron connection, I've just randomized them and done 50% random sparsity. Then you can pass this graph system G into ODE problem and solve that problem, and with a chosen differential equation.jl solver. And it will just go. So here's a messy GIF of what the solution to one of these systems might look like. So yeah, that's kind of all I've got to talk about on graph dynamics today, but I'll just quickly say a few words about what we've got planned next. I obviously still kind of sparse on the documentation, need to do more of that. We'd really like to support delay differential equations because there's a lot of models in neurobiology that need them. We don't support it yet. Currently, we only support one event per subsystem, but this is something that we don't really need, but we might want to at some point add ways to say, okay, this thing actually has 2 events, so you got to check both of them. Often we're kind of computing various things and storing it in some parameter in the middle of a simulation, like for lateral inhibition and stuff in the cortical striatal loop. We sometimes need to calculate, okay, which matrizome is getting more input, and then shut off the other matrizome or something like that. But when you do this, you kind of lose the history of what that computed state was throughout the thing by just overwriting parameters. And so we want a system for calculating computed states that don't come from differential equations and storing them and getting the history of those computed states throughout the simulation. And we also want dynamical connections. So for instance, with NMDA receptors, there's real dynamics happening basically in the connection between a presynaptic and postsynaptic neuron. And we can support this currently in graph dynamics by basically just adding an intermediate node between the presynaptic and postsynaptic block and then giving that thing dynamics. But it can be kind of annoying to go in and calculate. You got to add one connection from the presynaptic to the receptor, and then the receptor to the postsynaptic, and then often a backwards connection from the postsynaptic back to the connector. And so it'd be good to give at least this intermediate block access to both the presynaptic and postsynaptic states at the same time. these connectors. So that's kind of my roadmap for the near-ish future. And I'm happy to take some questions.
Wasn't there I thought there was going to be an adapter.
So I think. So I had a question about like the inputs and the outputs. So I think in your example you had this JCN,
thank you.
which was input. So, and then in the connection rule, if I understood it right, you could kind of add things to input that. So what are the outputs for that?
Yeah, so currently we don't actually put any restrictions on what can be outputs because we don't really need to. So in the connection rule, you're allowed to basically take any variables from the presynaptic neuron and send it into the input of the postsynaptic neuron. We just need the inputs to be of a fixed form because otherwise it'll be type unstable when we're looping over all these structures. But we need that fixed. But the outputs, we don't. That doesn't need to be constrained, basically.
Okay.
All right. Hello.
Introduce the next speaker. It's great to have David Little here, and he will talk to us about a large-scale quantitative EEG analysis of chronic insomnia. Good that I'm not an insomniac.
Great. Okay. So just to give you a little brief agenda, I'll talk a little bit about the scientific background for this project. I'm going to focus on kind of the Julia-related aspects of the project and get to results as I can. If there's more time, less questions, I'll share more of the results. I'm happy to talk about that. So first of all, there are a lot of people who've contributed to this project that I'm really indebted to. Many people at Beacon, many people at our collaborator at Dorsia, and then these are two of the publications that have come out so far on the project. It's been long and ongoing and lots of people working together. So just a brief primer, electrophysiology on electroencephalography. That's electrodes on the scalp that pick up weak signals in the brain. And just to give you a feel for what this kind of data looks like, I'm showing you here one of our kind of viewers of EEG data. This is some open data from the sleep heart health study, which I like to call SHUSH because that's easier to say than sleep heart health. So that's how I'll talk about it. So the first two electrodes on this are wake EEG with a bunch of noise from muscle movement and then eye blinks, and then somewhere kind of the little tiny squiggles, there's some brain signal. So we have to deal with a lot of noise in this kind of modality. And then this is more what sleep looks like. This is N3 sleep, where you get kind of larger delta waves, lower frequency, higher power activity. And because the signal is kind of noisy, you also see some high frequency signal, but that's mostly noise. So that's what EEG looks like during sleep. And traditionally, the way EEG is analyzed for sleep, you look at the different stages, you get these 30-second segments that some human has annotated, and then you compute some set of statistics over those 30-second labels. And so many kind of metrics that people have looked at historically for EEG sleep are these sleep stages and statistics thereof. And those are kind of referred to as macro quantities. And then there are the micro quantities, which are more signal-based events and summaries, not quantified by, or not easily quantified by visual human inspection. And we need some set of tools, algorithms, computers to compute. So we're going to be looking at those two different types of features in insomnia. And that is often defined as difficulty initiating and or maintaining sleep coupled with distress or impairment in daytime functioning. And it affects about 10% of the adult population, and it's primarily diagnosed through subjective report. So someone comes and says that they're having trouble and they fit these criteria. There isn't some other explanation for what's happening, and they get labeled as someone with insomnia. You might think that EEG would be a good modality to help diagnose this, but there are a few challenges. So there are inconsistent findings in kind of what objective properties matter for insomnia, and part of this is about the difficulty of interpreting EEG as a human. Many of the traditional studies are using these macro quantities. So that doesn't consistently identify those with insomnia, at least in kind of small N scale studies. And there's also a lot of burden for performing EEG traditionally. So one normally uses in-lab polysomnography for a sleep study, so that includes EEG and a variety of other measures. It's in high demand. There are multiple month delays to get into a lab to get that kind of study. It's invasive. You're not sleeping in your home environment, so external validity concerns arise. And it's labor intensive. You need a technician who's well trained, and they need to be there the whole night to monitor the equipment. So here, our hypothesis is that patients with insomnia exhibit quantitative EEG microquantities that are indicative of a state of hyperarousal, aka there's some aroused-ish state of EEG. And we're going to analyze that across 3 large data sets to test if that's the case, if we can look at this in a more objective way than we've been able to in the past. So just to give you a sense of what I mean by large, what the scale is, a typical EEG data set, at least for a sleep analysis, is on the order of a few gigabytes. And here we're working with about 13,000 total files, so about 2.6 gigabytes of data, 3,000 roughly recordings in the final analysis, and about 168 sites. And the number of sites really matters for the complexity of data ingest. And those also include some at-home recordings. So in terms of existing insomnia studies, this is the largest so far. And so now I'm going to move kind of into like methodology, like how we did this in Julia, and some of the challenges we faced there and how we address those. So ingesting data at this scale is very messy and heterogeneous. EEG is very noisy, and there are a lot of common features that we want to use that are fragile to noise. So a lot of this work involved ingesting data, visualizing it, validating it, and iterating until we get to the final stage of the actual analysis. So a way we thought about this, think about this throughout a lot of our projects, we try to take a very incremental document approach. So each step of the ingest or curation or analysis is a self-contained reproducible Julia script. We document that in some README for each step, located in subfolders. We have each data version and some deliverable date for the actual reports and figures and stuff that we're making. And that's all organized through a package that Beacon developed called Legolas.jl that's open source to organize schemas and validation of them, named tuples with well-defined constraints. And then we programmatically retrieve that in terms of the schema and the data versions. So we always kind of know where we started in an analysis, and we have good documentation about each of those steps, as there's tends to be quite a few of them. And in terms of the role Julia played here, right, there are a number of wins. So Julia helped us with having a reproducible project. That's very straightforward there. There's a lot of great language interop, which is really helpful with the vast number of esoteric file formats we have to deal with. So we use a lot of like just simple arrow interop with some other language or Python call or just shelling out. And just the ability to tinker. There are often details of the signal processing that matter for dealing with the noise or some hot loop of file parsing, and being able to go and mess with that and have it in the same language when we actually have the libraries for that. So kind of the flip side of that coin, both those things are really handy. And there are a variety of packages that we really benefited once we get to the analysis. Mixed models lets us do the kind of analysis we want across a lot of different features, across a lot of different recordings in like a sane amount of time in a way that we wouldn't otherwise. So models per minute instead of minutes per model. We use effects to visualize and interpret those results. Mach-E, of course, is really helpful. We have a lot of flexibility in terms of thinking about loss functions with Flux for the kinds of analyses we want to follow up with, and for more standard pipelines, once we got past the learning curve, the MLJ. So these are all things that have been super helpful to us in this analysis. And we also faced a lot of challenges given the scale of this work. It's not like quite big data the way it looks. Sometimes we call it inconveniently large data. And so, compilation time was a big thing, especially circa in the eras when we were most intensely working on this analysis, 21 to 23. But of course, there have been huge gains there. Distributed and computing and deployment has been a real pain point for us, and a lot of that now resides on like individualized teams. And this project was in a very kind of early phase of the startup of my company, so we did kind of a lot of this on our own. And then we've kind of moved to dedicated teams to deal with those warts, largely in language agnostic ways that don't leverage the Julia ecosystems for those particular things. We had a lot of challenges with Arrow early on, largely about the kind of early way that caching was handled there that have been kind of addressed subsequently. And AWS is often kind of a pain point for a lot of this when we're working with the large files and dealing with kind of the mismatch between a kind of key value store that system really is and the directory abstraction that kind of gets tacked onto it. So to get to some of the like results here, once we were able to kind of ingest data and make sense of things, one key finding here was that I think really highlights the hypothesis I was bringing up earlier. Not all the sleep stages are created equal, if you will, when you're looking and comparing those with and without insomnia. So this is a wake EEG similarity index that we use. So it's an aggregate data-driven measure of the arousal state in EEG. And what you can see here on the x-axis are the sleep stages. So you've got wake on the left, and then you've got N1, N2, N3 in REM. And then the green is individuals without insomnia, and the purple is those with. So those with insomnia show strong differences in the arousal state during wake, and then some differences in N1, N2, and REM. So what that means is that even though they're being classified as the same sleep stage, we see notable differences in what those look like for those with insomnia and without. So I've still got some time. So this is kind of a summary of what we've gone over so far, right? To scale this kind of project, we had to use, the way we found that has really helped us is to use very small incremental migrations, visualize thoroughly, document thoroughly. Julia really helped us in terms of its reproducibility and flexibility. And the many fast and reliable packages were super helpful in the analysis process. And then we see here that there are quantitative shifts in EEG within sleep stages during insomnia. And the direction of those shifts are consistent with the idea that there's some hyperaroused state, which is pretty straightforward as a notion, but the fact that you can see it within sleep stages is a novel finding and important in terms of our ability to objectively characterize this. So, where are we going this? Why do we want to be able to look at quantitative measures of EEG? There are a variety of at-home systems, including beacons. Ours is called the Waveband, and it's validated against gold standard in-lab PSG. So the sleep stages you get out of that are quite close to the sleep stages you would get from an in-lab study. And that's easy to deploy at home, which means that we have a scalable system due to the low burden in-home recording. And that, again, leads to greater external validity. It means that we have Sleep itself can be a quite stable indicator of a variety of diseases. There are many sleep disturbances in a number of diseases, not just the ones that would be obvious like insomnia or narcolepsy, but also things like depression or Alzheimer's or schizophrenia, which might be less obvious. And it gives us a means for stratifying those populations and moving closer to precision medicine, where we're looking at an individual's particular state to make decisions. And keep in mind, all these diseases are largely defined in terms of their symptoms, not their causes. So heterogeneity is it's inevitable. So being able to deploy at scale a means of starting to parcel out these groups into smaller, more objective units, I think is a really exciting possibility. And I'll move to some of the, I thought that's how far I would get, but it seems like I have a little more time. So I'll talk a little bit more about the results, because I'm excited about those, and hopefully you'll find them interesting. So I'll talk a little bit first about this method I was describing with the results before, called the Wake EEG Similarity Index. And that's actually a pretty simple method. We look at 33-second epochs of the EEG spectrogram. We break that into bins of the spectral power. And then we look at the sleep and wake state based on the hypnogram. So that's in 30-second chunks to create a label for each of those 3-second units. And then that gives us, via robust logistic regression, some estimate of the probability of a given 3-second segment being wake. So this isn't used to decide whether the segment is wake or not. It's a continuous estimate that gives us some sense of arousal state. And we get pretty good AUC, indicating that we're appropriately differentiating wake and sleep from the 30-second labels, which we don't expect to be perfect, right? Like each 30-second segment is likely to have states in it that are wakeful or sleep-like. It's just that the human labelers are giving it in 30-second sections. So with that continuous measure, we then use that to look at the average of that signal in the individual sleep stages. And that's where this figure that I showed you before comes from. We also looked at this in an interventional context. So now, with our collaborators, we worked with their data set where they're treating insomnia. And the idea here is that there are orexin neurotransmitters, A and B, that are hypothesized to promote wakefulness cycles by supporting the transition from motivation to behavior. There's plenty of details there that I'm glossing over. The kind of oversimplified story here is more erection leads to more wakefulness. And so there are a number of class of drugs called dual orexin receptor antagonists, or DORAs, that block the effect of orexin, reducing wakefulness, and that can be used to treat insomnia, under the assumption that it is something about this aroused state that matters for insomnia, which probably matters for some patients and not for others. And so when we look at the intervention, we see a similar pattern where the treatment of insomnia leads to a more normalized state of the wake periods around sleep. So we see decreases in wakefulness in the wake periods for those who are treated that looks reasonably dose dependent. So yeah, I will stop there. I have plenty of other things to share results-wise, but if you have questions, I think it's a good time to pause and take them. Great.
Can I actually start with a question? So I was always intrigued by sleep staging. So I looked into this a little bit, and there's lots of studies that usually the ground truth or something like this is like if some specialist in sleep staging stages the sleep off an EEG, and there's actually studies that show that if you show the same data to many different sleep stages, then you get maybe 60% agreement. And how did you solve this problem of saying that you get the same results as a professional sleep study that uses professionals to sleep stage?
Right. So yeah, there's a like inter-rater agreement measurements that we look at. And so, we'll get 3 raters to rate each recording, look at kappa, and then there's the model's agreement with each of those raters. And so if the model is kind of in better agreement, or as good an agreement as any one of the human labelers, then we call that model kind of at human performance. So, right, any one stage is not going to be perfectly classified by any one of the raters or any one of the models, but the model is going to give you kind of the average of all of those raters.
I always thought actually that machine learning or unsupervised machine learning would be a much better way of figuring out how many sleep stages there actually are, right? I mean, in principle, if you don't have to fight the medical personnel, right, on this, it's probably much easier if you come up with a classification.
Yeah, I mean, right, I think what you're hinting at is like having some kind of foundational EEG, the LLM of EEGs, right? And then using those kind of features to somehow show that they're more objective or more representative of actual brain states in some way, right? And I think the challenge there, of course, is finding a way to validate that, to show that like it has some meaningful clinical difference that makes it superior to the sleep stages. And I agree, there would also be a lot of like cultural resistance to that. And so the obvious place to start there is showing that you can do what the doctors can do and help them save their time, and then kind of move to making it better. Oh, so that's actigraphy. Yeah, so, the question was, how does my watch work? He's showing an Apple Watch that gives you sleep staging. So that's actigraphy, and it's basing it purely on movement. So that does a pretty good job of differentiating wake versus sleep, and it can make guesses about the sleep stages. It has a very difficult time with REM, so rapid eye movement sleep, which is quite important to a variety of disorders. One of the key biomarkers, we think, of a lot of these disorders are the shifts that happen in REM, the delays or suppression of REM. So knowing if there's a REM or not really matters for diagnosis. The watch is great for something like sleep apnea, where you want to know more kind of like level of activity. But if you care about REM or like details of the micro features, which is what I'm showing here, the watch isn't going to tell you that.
Hi, Yes. Hi, I was wondering, were there any non-spectral features you considered looking at with your analysis? I'm asking as another EEG researcher.
Yeah. So we looked at quite a few features. This is arguably very much a fishing expedition, right? There were thousands of features we looked at. They included spindle features, they included spectral features, various statistics thereof. There are various details like micro features of like REM that we didn't look at, like you can look at REM density, for instance. We didn't look at that. The spindle features are kind of interesting. We saw changes in the retrospective cohorts when we looked at those, comparing with insomnia. But when we looked at the intervention with DORA, we didn't see changes in spindles. So that's kind of a weaker result, right? Like that could be because the drug isn't treating it, or it could be because there's some other problem with the retrospective data that we didn't identify.
Yeah, that's very interesting. I was asking because so I work with sort of anesthesia EEG, and one of the big things that we care about, or starting to really try and parse out and understand how to analyze, are individual variation across, so in anesthesia, right, the traditional thing you get is an alpha rhythm in the prefrontal cortex, and that alpha rhythm can be centered in very different places for very different people. And so I was sort of wondering, to what sort of extent did you feel limited by your sort of band analysis, and what would you do next?
Yeah. I mean, there are so many things you could, like so many features. I think that's part of the challenges. Like, it'd be nice to have like a hypothesis-driven, like, here's why I'm picking this feature. But in insomnia, it's challenging because it's so heterogeneous. Like if you had some really good causal explanation, it'd probably apply to like 25% of the population, and you're not going to see it in the mean result. I think, right, there's lots of things like FOOF, for instance, where you're like fitting some curve to the spectral analysis where, I think you'd be getting more at what the spectral power means. I think that would be nice.
Yeah, okay. Yeah, thank you very much.
Yeah.
Quite a bit of time, so until the next speaker.
Yeah.
Do you do anything on like medications that people use for sleep? I mean, it's like, except for Dora, but other things. I mean, it's that there's a lot of over the counter and.
Yeah, so the data that we have is pretty rich that way. When we were selecting down to the 3,000, we picked the subset we chose based on, keeping out medications that might also cause sleep to change in various ways. Like we didn't include people, I think, with melatonin, for example.
Right.
There's a rich repository of opportunities to look through that and find and ask other questions, I think.
But you could, for example, tell whether some sleeping medications for sleep will actually help you or just knock you out, right? I mean, whether it's actually healthy sleep or whether it's just...
Yeah, so that's one kind of argument from the paper that looked more at the intervention, right? It's in many other ways the drug did not change sleep, and you see with a lot of other medications that aren't these DORAs, like kind of more traditional, like Ambien or something like that, where there are huge changes in what the sleep looks like. There's a lot of beta rhythm, for instance, and it's not clear that that's actually great sleep at all. So a kind of bonus or like advantage of this drug seems to be that it is mostly helping you to get to sleep and then not changing the features of the sleep once you are asleep.
It gets you over the first hump, right?
Yeah.
What you're essentially saying is that the first sleep stage is the hump. And if once you overcome this one, then you're going to sleep and you stay asleep.
Right. For at least the people for this drug for whom this drug helped.
Okay. That's fascinating.
Cool.
Fascinating. Okay, so let's set up the next speaker. I think you're the next speaker, right? You're at 4:30.
Thanks, everybody.
Just make sure that all the computers work. Yeah. Plug it in. How does it work? So we're not exactly offline.
I think that's up.
We should wait until some people
Yeah. Okay.
I didn't understand what you meant by deck.
Oh. Yeah.
And the way this works is that you get shown like 5 minutes. If you have 5 minutes left, then it shows you 5 minutes left and then 1 minute left.
All right.
So you may want to time it to be like around 8 minutes. And then if you want questions, then
Oh, okay. All right.
then make it like 8 minutes.
Okay.
And then let me actually check. be on neural ODEs. This is actually a Shiv Davai, and he's actually from the Thomas Jefferson High School of Science and Technology. So he will tell us about his work, and go ahead.
Thank you so much for your introduction. So my project is Neuro ODEs, modeling synaptic tagging and capture dynamics, and I'm a rising high school junior at Thomas Jefferson High School for Science and Technology, so pardon me if I make any mistakes because I'm still a novice in the field. So to start off, I'll go over a brief roadmap, starting with my introduction, then the motivations and objectives, then I'll move on to my methods and results, then I'll talk about key findings and the significance of those findings, then I'll move on to like my limitations, future work, and then key conclusions and takeaways. So to start off, thousands of researchers have been creating ML, machine learning-based diagnostic systems. Now the question arises, why aren't machine learning-based diagnostic systems adapted into clinical environments? First of all, there's a high risk for medical errors. First, there's over $250 billion spent annually because of medical errors, and over 20 million people are affected because of it. This can include misdiagnosis and also medication errors. For example, people living in rural areas that don't have access to proper healthcare systems in comparison to people living in urbanized systems, they don't have access to proper healthcare, they don't know how to treat rare diseases, and there's a lot of error because of that. Also, HIPAA policies make medical data inconsistent and hard to analyze, which is why many algorithms are unable to train properly on it. So moving on to the next portion is why ANNs are foundationally incorrect in terms of a biological relevance. It's because in terms of neuroscience principles, there's different mechanisms involved. For example, backpropagation, it works bidirectionally while accessing the entire neural network, whereas neurotransmission works in one direction, it's unidirectional. So as mentioned before, my motivation was 30 million Americans are currently undiagnosed or misdiagnosed with various conditions with no cure or treatment plan existent. And recently I read about how Geoffrey Hinton won the Nobel Prize in Physics for his work on backpropagation. So my research objectives included addressing the biological implausibility of backpropagation in modeling memory consolidation and synaptic plasticity mechanisms, and to create a framework in doing so while achieving a high prediction accuracy. And I wanted to ensure that the model follows a top-down approach rather than a bottom-up processing to ensure that it matches synaptic plasticity and memory consolidation. So as a result, my research question was, can prospective configuration serve as an effective alternative to backpropagation for modeling the STC hypothesis, and would using Julia over Python offer advantages in solving the associated ordinary differential equations? And I hypothesized that both of these would be plausible. So first of all, let me talk about some key limitations of backpropagation. So first of all, it violates Dale's principle, which states that neurons can't be both excitatory or inhibitory, so it has to be one of the two. And because of this, backpropagation uses global error signaling to be able to optimize the learning patterns and the weights properly. And moving on to the STC hypothesis, it is supposed to model memory consolidation and long-term potentiation, and it is a critical mechanism for doing so. And the three features that I used in coding my neural ODE were time, synaptic strength, and protein plasticity-related protein concentration. And here are the two ODEs in my mathematical framework. And here are like all the variables describing what they are. So explaining about just me giving my version of what I think a neural ODE is. They're an extension of neural networks for continuous time domain, and they're able to handle irregular time series data. For example, in the STC hypothesis, protein concentration is far more variable than synaptic strength, so having a model that's able to capture both types of data is very important, which is why neural ODEs were optimal for this project in comparison to other algorithms that I could have tested. And moving on to the alternative learning mechanism that I intended to use in this project, prospective configuration. It solves a pattern because it only uses a forward-only weight optimization algorithm with local prediction errors and dynamic weight adjusting, and it operates without explicit backpropagation of any errors. So the key Julia resources that I used were differential equations. The key packages that I used were differential equations, flux, and plots. And here's a code snippet of the neural ODE that I coded. So here at the beginning is my neural network architecture, in which I had cubic transformation to assess for biological nonlinearity. And then I had 2 hidden layers, and then my output layer condensed my 50 neurons into the 2 results that I wanted for synaptic strength and protein concentration. And here are my neural network parameters, and then here's my neural ODE, which is taking into the time span, and then it uses the ODE solver, and then it saves all the solutions at these time points. And here's my loss function as well. So I had 2 synthetic data sets throughout this project. One was a clean data set, and one had Gaussian noise to mimic biological variability. And on the right side is the figure with the Gaussian noise. As you can see, the protein concentration is incredibly variable, and the synaptic strength, which is the connection between 2 neurons, is far more gradual change. So having a model that could model both of them at the same time simultaneously is something that I intended to have. So the final neural ODE model architecture, in combination with perspective configuration, consisted of the neural ODE along with perspective configuration. And I tested variable training testing splits like 80-20, 70-30, and 60-40 to find the best optimal fit. And then I defined my initial conditions, and then I implemented perspective configuration, and then I used different optimizers and combinations of them, a BFGS, AtomW, Atom, and RMS prop, because those were key optimizers that I'd found that were used in previous literatures. And so I had 14 different experiments when I was training for hyperparameters, and experiment number 7, which was a combination of AtomW and BFGS, turned out to be the best one. So in terms of my results, here are my results with 80-20, 70-30, and 60-40. So this 80-20 had the best results with an 89% of accuracy, which is significantly higher than the baseline, which is set around 70 to 75%, depending on what type of model you're using. And this is another graph showcasing the loss in accuracy with regards to time and epochs that I trained it on. And the statistical analysis showed that the predictions were extremely close to the actual data, which showed that this model has a huge future, and it can be used, and it can successfully replace backpropagation. And the key findings were that neural ODEs were able to effectively model synaptic dynamics, and it was able to remain stable even when Gaussian noise was incorporated to mimic biological variability. And I was surprised because hybrid optimizers were not something that came across very much when I looked in the previous literature. And I just tried it just because I thought it could work maybe to optimize it further. And it was something that worked and improved accuracy more than expected from I was in the 81 to 82 range, and it went up to the 87 to 89% range in terms of accuracy. And it captured the complex interaction between synaptic strength and protein concentration. So some constraints that I had throughout this project were there were no in vivo based recordings that I had, so I had to use synthetic data sets to do this. And there's a high computational cost because I ran all of this locally. I didn't have access to a supercomputer, and I didn't have any university-based connections that I could utilize to work at this further. And the conclusion was I was able to accurately model the STC with an 89% accuracy, and was able to ensure that my results were biologically relevant, and I was able to validate that prospective configuration is a valid alternative for backpropagation, and I was able to also build an efficient neural ODE architecture optimized for synaptic modeling, and I laid the groundwork for disease modeling and neuromorphic applications. And future work is I want to simulate progression of certain neurodegenerative disorders, such as Alzheimer's. This is an app, I would say, that I kind of just built, and I just wanted to add an image of it, is something that could be used in a clinical environment when patients are being compared between having Alzheimer's or not. Because of synaptic degradation, the protein concentration decreases with regards to time. So a control patient is going to have a lot more proteins that are, with regards to neurotransmission, that are transmitted, and then the synaptic strength will still be gradual change, but it'll still be between 50 to 100%, which is what 0.5 to 1 means. Whereas you can see in the Alzheimer's patient that the synaptic strength is decreasing with regards to times, and so is the protein concentration. So yeah, and I want to, in the future, work towards modeling STDP, which is another plasticity-based mechanism, and also validate this model with potential electrophysiology recordings from rats or humans as well. and accelerate training using better computers as well. So yeah, thank you.
Yeah. So your implementation. So did you also use backpropagation and see how much faster backpropagation is than forward?
Yeah, so I used both. I tested both backpropagation and so I tested efficiency as well in terms of backprop and what do you call it? Perspective configuration, and then I tested it in both Julia and Python to see which one is more efficient. And as you can see through this figure, Julia is far more efficient because it's meant for scientific machine learning. It's meant to handle these ordinary differential equations.
Okay.
Yeah. Thank you.
So I'll introduce the next speaker. So Herman, and I never know how to pronounce your last name.
Yeah, Abrevasha.
Abrevasha. I just made this up. So so he's working on deep brain stimulation. So we created essentially a model for actually ERNA, right? And he's going to tell us about it. And you have the same problem.
Nothing. No, it doesn't detect. It is not detecting the. It is not open. Hi, my name is Germán Abrevalla, and I am a staff scientist at Neuroblocks. And today I will present to you some of Neuroblocks' capabilities for modeling deep brain stimulation. But first of all, what is DBS? It is a treatment for various neurological disorders, such as the Parkinson's disease, and you can think of it as some kind of pacemaker, but for the brain. Here in this image, you can see an electrode implanted in the subthalamic nucleus. And in general, there are some beta oscillations, which you can see here in the power spectrum, that correlates with some of the Parkinson's disease symptoms. And that's why it is usually used as a standard biomarker to guide surgery, to guide the positioning of the electrode, and also to guide the DBS programming afterwards. But it has some practical limitations. For example, it doesn't correlate with all of the Parkinson's disease symptoms, such as the tremor. It doesn't correlate with tremor. Also, it is susceptible to the microlesion effect, which is a temporary improvement on the symptoms, but only due to the lesion done during surgery. And also, it is unreliable during general anesthesia. But in the past few years, there were some new biomarkers that were identified, which could potentially complement beta oscillations. And these are some spontaneous high-frequency oscillations that you can see here in the power spectrum, and some evoked resonant neural activity, or ERNA in short, which are the focus of this talk. So ERNA are some transient oscillations that emerge about 4 to 5 milliseconds after each pulse. Their amplitude builds progressively with the train of pulses, and then decay after the end of the stimulus around 30 milliseconds after the end of the stimulus. They have some remarkably high signal-to-noise ratio, and most importantly, oftentimes the positioning of the electrode that generates the maximum ERNA amplitude coincides with the positioning of the electrode that makes the treatment more effective. So those are called the therapeutic sweet spots. However, the actual biophysical sources of ERNA are still unknown, as it is the relation with ERNA and HFOs. But what we are most interested in is in how to use these new biomarkers in order to inform the surgery, the positioning of the electrode, and also the DBS programming in order to get the most effective treatment with the lesser side effects. So, but despite the effectiveness of DBS, it is still vastly underutilized in the world. And one of the main reasons is the complexity of the DBS programming. Currently, it is still some kind of guess and check process in which the patient has to go to visit the clinician, the neurologist, every few weeks. The neurologist change some parameters, then the patient go back home and check if the symptoms are better or worse, and then go back to the neurologist. So it is quite cumbersome. And these new biomarkers could potentially help and benefit both patients and clinicians. Patients would have greater and increased access to this treatment, also more efficacy, and a reduced number of the programming visits. Clinicians would get more robust tools to guide surgery and also more effective and simpler tuning. But moreover, the whole scientific community would benefit by an increased understanding of the principles of action of DBS. So here at NeuroBlocks, we're developing a DBS module, and in particular, we're creating some minimal ERNA model, which aims to be not only biomimetic, but also computational efficient, so that you can tune the model to experimental data and create patient-specific models. So the first step for this was to create a simple DBS stimulus blocks. These are just square stimulus, in which of course you can tune all the basic parameters, but also the smoothness of the stimulus, and also compute the transition times, which would be useful later on to pass those time points to the solver as the t-stops and make sure that the solver doesn't miss the changes in the stimulus. But we also implemented some protocol DBS, matching the parameterization that clinicians use. For example, this is blocks of stimulus, and you can change, of course, the number of bursts per block, the number of pulses per burst, etc. And then we were developing a biophysically detailed model of what it is believed to be the dynamical core of ERNA, which is the feedback loop between GPE and STN with some cortical input to excitatory cortical input to STN, which is modeled by an Ornstein-Uhlenbeck process. And the GPE and STN neurons are modeled with the classical Hodgkin and Huxley model. So in particular, we model the DBS effect, the stimulus effect, directly in the connections that are known to be affected by the stimulus, namely the cortex to STN, STN to GPE, GPE to STN, but not the GPE collaterals. So here you have some classical conductance space synaptic current. S sub k are the synaptic gating variables. And here in this rate function is where the DBS comes into play. So this is a plot of this function, and you can see that when the neuron is not firing, so it is at its resting state, this function tends to 0. If the neuron fires, it increases its value. but also if it is not firing and you have stimulus, it also increases. And with this set of interpretable parameters, you can tune the sensitivity of the model to the stimulus, which would be to tune the response, the dose response curve. So let's see some results. Here on the left, you have some experimental ERNA measured by our collaborators at MGH, the Massachusetts General Hospital. And on the right, you have some results from our simulations. These are some average over 200 simulations. And even though the shape is not exactly the same, you can already see that this is still a work in progress. You can see that it already recovers the main features of ERNA. Like the very basics is that after each pulse, you see some evoked pulses, evoked neural activity. Also, the amplitude of the peaks starts to increase, builds up with the train of pulses. And you can see also this second peak here, which builds up progressively with the train spikes. So we learned a bit about deep brain stimulation therapy and how it can help to alleviate some of the Parkinson's disease motor symptoms. We saw also the simple stimulus blocks and the protocol stimulus block. And I presented a minimal STN to GPE model that reproduces ERNA. So some next steps could be to develop an equivalent population model to make the simulations faster and more proper to be incorporated into some optimization procedure and in order to make some patient-specific models. And also, most importantly, to add the spatial dimension to the model so that this model could be used to guide the surgery and the positioning of the electrode. So ultimately, NeuroBlocks proved to be a simple, flexible, and performant tool for doing neuroscience research, and in particular, perfect to develop models of deep brain stimulation. Thank you very much.
Question. Nobody wants to add a question? If there are no questions, then we'll thank him again.
Thanks.
The speaker is Ryan, right?
Zachary.
Oh, Zachary, that's the second one. Zachary Lashinsky. And he's going to give a talk on state-space dynamics.jl. It's a probabilistic state-space modeling toolkit. And I'm really excited about that.
Okay. All right. Hello, thank you for the introduction. I'm Zachary. I'm a PhD candidate at Boston University. And we've been developing this package for probabilistic state-space modeling in our lab for a little over a year or so now. And we're excited to come here and share what we've done. So I'm sure a lot of you are familiar with state-space models just from the conversations I've had with some of you. But in general, state-space models are just probabilistic models that are used to describe time series data. They include a wide range of models like hidden Markov models and dynamical systems. But the unifying assumption here is that observations are generated from a hidden or latent process that you don't see. And these models have applications across many different domains, such as economics, robotics, but we're all here to talk about neuroscience, where modern neuroscientific tools have enabled the collection of huge, like unprecedented amounts of data that are high dimensional and time series. And state-space models are a great way to combine both dimensionality reduction and temporal dynamics into one model. So this is the basic vanilla graph for state-space models. For those of you unfamiliar, you have a state variable that typically evolves according to a first-order Markov chain. And at every single time step, those state variables give rise to a set or a single observation. This very simple graphical model allows people to build these really efficient recursive algorithms for doing inference in these types of models. Many of you may be familiar with Kalman filtering and smoothing, and maybe forward-backward for hidden Markov models. I'm seeing lots of nods. That's great. So for example, if you had continuous state variables that evolved linearly and Gaussian emission models, you'd end up with something like a typical dynamical system. Whereas if you plugged in discrete state variables that evolved according to a categorical distribution, and maybe you still had Gaussian emission models, you'd end up with something like a hidden Markov model. Okay? All right. So SSMs have been used historically in neuroscience for many different reasons, but I've just highlighted 4 examples that I find pretty cool, kind of divided roughly into animal behavior and understanding neural dynamics. So within animal behavior, state space models have been used for understanding animal learning and quantifying animal uncertainty during behavioral tasks. They've also been used for classifying animal engagement states, whether an animal is super engaged in a task they're in, whether they're just biased, maybe they don't even care anymore and they're just kind of conked out. That's really important to know when you're doing data analysis, and state space models have enabled us to do that labeling. And also for neurodynamics, some cool examples of state space model applications include identifying fixed points and preparatory areas for motor activity that seem to be setting initial conditions for the dynamical systems that control movement. And also this really interesting example from David Anderson's group that found a continuous line attractor that seems to be modulating aggression behavior in mice. So pretty cool applications, kind of all spread out. This is by no means an inclusive list, but just some cool things. There are some existing Julia packages for doing this type of modeling. Some of you may be familiar with that if you work in the space, such as hidden Markov models.jl, state space models.jl, and then Turing.jl, which also provides some tools for state space modeling. Hidden Markov models.jl, as the name kind of implies, was built for discrete state space model functionality, whereas in neuroscience, we also are really interested in dynamical systems. So this didn't quite fit the bill for what we wanted to do for our analysis. This state space models package, or state space models.jl, does have continuous state space model functionality. However, it's limited to linear Gaussian, kind of classic vanilla dynamical systems models. Whereas in neuroscience, we'll see that it's pretty important to have support for things like Poisson and Bernoulli distributions. And Turing.jl provides many different sampling methods that you could use in theory for doing state space modeling and inference. However, these sampling methods can be quite slow compared to inference algorithms that recursively kind of take advantage of that graphical structure. So where do we fit in? We have built tailored algorithms for discrete, continuous, and hierarchical state space models with extensions to non-Gaussian emissions. Now I want to highlight here that our goal is to develop these hierarchical state space models and extend the functionality to non-Gaussian emissions. We do have some redundancy here with some of the other packages that we're working diligently to interface with now, like hidden Markov models.jl. These were solely built as a means for us to get to our real design target. So put simply, our goal is to provide a set of tools to neuroscientists that need state space modeling in Julia, build functionality for non-Gaussian models typically found in neuroscience, such as Poisson and Bernoulli, and then provide functionality for hierarchical state space models like switching dynamical systems, recurrent switching dynamical systems, these type of things. So, put kind of plainly, our current functionality is Gaussian dynamical systems, Poisson dynamical systems, switching dynamical systems, and then also hidden Markov models, and even these generalized linear model HMMs, or switching regression models. So I'll just jump into a couple examples. The first being a Poisson dynamical system. On the left, you're seeing samples from a Poisson dynamical system we've built using our package. You can imagine you have 10 neurons here on the bottom left of your screen, all kind of spiking, and their spiking is dependent on these 2 continuous latent variables that you see above them. On the right, we initialize a new Poisson dynamical system, and then we use expectation maximization to learn the parameters of that model from the observed data. And then we do inference to see if we can recover the latent states correctly. And look, we do a pretty good job. Reasonable accuracy, depending on how warm of a start you get it, but reasonably good job. And I want to highlight here that the inference method that we have is really what enables us to use non-Gaussian emission models and handle this type of data you would want to in neuroscience. This is a method that's been known for a long time, kind of, I think, in the statistical literature, but was kind of brought to neuroscientists' attention by Liam Paninsky quite some time ago, where instead of using Kalman filtering and smoothing to find posterior state paths and map estimates, we actually directly optimize the complete data log likelihood with respect to the state paths using Newton's method. Now, what's interesting about this, or what's I guess maybe obvious to some people about this, is that in a linear dynamical system where you have linear dynamics and Gaussian emission models, This likelihood function is quadratic, and Newton's method will converge in a single step. So actually, this is just as fast as the same time complexity as Kalman filter smoother, and it's mathematically equivalent in the linear Gaussian case. However, this is flexible, and it allows us to move to nonlinear emission models and non-Gaussian emission models. In the typical recursive algorithms like extended Kalman filtering or unscented Kalman filtering, you'll have to construct all of these local approximations to the map estimate. Whereas here, if you have a Poisson model and then you iteratively run Newton's method, you can get the exact map estimate even for non-Gaussian emission models. Once we have this map estimate, we can construct the posterior distribution through a Laplace approximation. Basically, we construct a normal distribution centered at that map estimate with the inverse of this Hessian matrix as the covariance. Now, again, if you have a linear Gaussian model, this will be the exact posterior because the true posterior is a Gaussian distribution. Now, some of you may be wondering, well, look, you have to invert this matrix. What is this going to do? Well, because of the graphical structure of state space models, this is actually a block tridiagonal matrix, giving it a very special structure and allowing us to do all of these things in linear time because you don't have to invert a huge full matrix. You just have these 3 bands. And people have developed really efficient algorithms for handling that for us. So great. Okay, switching gears a little bit, no pun intended, to the switching dynamical systems part. We've implemented a structured variational inference approach for learning in switching dynamical systems. For those of you unfamiliar, let's say you had a nonlinear system that was switching between, oscillating in some dimensions, then to another, and then kind of going back and forth. You can approximate these dynamics in a piecewise linear way by fitting a switching linear dynamical system, where this is simply the graph of a dynamical system, and you've added this discrete variable kind of under it to control which dynamical system you're generating observation from at any moment in time. There were labels. Okay, I already explained that though. So here's an example of using our package for switching dynamical systems. On the left side, you can see hopefully in the background there's colors that indicate which discrete variable is being used or which dynamical system is active at any moment in time. And in the front, you can see 2 continuous latent variables that are being generated. And in this particular case, we have a high frequency mode and a low frequency mode that we're switching in between for generating data. But pictured here are only the latent states. And on the right, you can see after doing parameter learning and structured variational inference, we recover kind of the low frequency modes and the high frequency modes fairly well, but there's still some definite room for improvement here on the amplitude side, and we think switching to a different method might help us out. Okay. In the future, like I kind of hinted at earlier, we want to interface more directly with hidden Markov models.jl for our HMM functionality. That's an amazing tool that came out while we were developing statespace-dynamics.jl, and we're working to take advantage of that tool. It's amazing. We would also like to implement more hierarchical state space models, like recurrent switching dynamical systems that people have found to be pretty interesting when trying to understand how neural dynamics give rise to computation. And we would like to move towards a variational Laplacian approach for our hierarchical state space models, as we think they'll solve some of the issues we're having with structured variational inference. And we're currently in the JOS review process, so woohoo, that's pretty cool. All right. I'd like to just primarily thank the lab the DePasquale lab who has been developing this project, primarily Ryan Senni, who's unable to be here today, but has really spearheaded this effort and kind of shown me the ropes along the way. And thank you to the Julia community for being so welcoming and helping us out.
Wonderful. Thank you so much. So other questions? Anybody has a question? So actually, so what you call the Newton method looks like the Gauss-Newton method, or there's a difference, or
that may be.
That may be right because because Gauss-Newton method is just the derivative, right? But this is the Gauss-Newton method. Okay.
You're correct. Yeah.
Okay.
Thank you.
Okay. So thank you everybody for coming. This concludes the Neuroscience in Julia mini symposium. We didn't have so many participants, but we had very active participants, so this is also good. And we are just trying to form a community in Julia. So it will get better, and this is just the start. So thank you again for coming, and have a good evening.